Well, let's when we kick things off here. So my name is Leif Hauge. I'm a senior civil engineer for Waukesha County's Department of Parks and Land Use, and I'll be serving as the moderator for today's workshop. This is, I think, our 24th annual Stormwater Workshop. It covers a broad variety of subjects. I'm not going to try and list them all. The workshop is this morning until about 11:30, and then again tomorrow from 8 to 11:30. The presentations are mostly about a half hour long. Try to keep things moving as much as possible. If we get a little ahead in the schedule this morning, we have one short poll mostly about who the attendees are. We post all the presentations we receive as PDFs on our website. Kelly, I believe, is going to be showing a URL to log into that website. Right now, I think there are 4 presentations posted there in case you're interested in trying to follow along. We've had some requests to do that in the past. We do offer PDHs. To get one, you need to respond to an email that Kelly from Wisconsin Land+Water is going to send you after the workshop that contains a link to an evaluation survey. So fill that out and then you'll get your PDH certificate emailed to you. I'm going to give a little background on each of the presenters. If you have questions, and I hope you do, please submit them using the chat button at the bottom of the screen. I'll keep an eye on that and either pass them on to the presenter directly or at the end of their presentation, and hopefully we'll reserve about 5 minutes for that. The Q&A button that you see, that's more intended for internal logistical purposes. I'm going to turn my video off while the presenter's talking, and Pete, when you're getting down to about 3 minutes, if it's getting tight, I'll turn my video on. That'll be a sign that you're getting close. I want to thank Rick Eilertson from AECom. He offered to do a half-hour ethics presentation as part of, it's one of the last presentations tomorrow. So if you tune in, you can credit that towards your ethics requirement for professional development if you need it. So Pete Wood is a water resources engineer with the DNR. He's worked for the DNR since 1991 and has been with the Stormwater program since 1998. What did you do before that, Pete?
I was in the drinking water program.
Oh, okay. Currently, Pete reviews erosion control and stormwater management plans for projects in Southeast Wisconsin. And I recently found out that he's an accomplished guitarist and singer and performs in a duo. So, Pete,
yes.
You're going to do regulatory updates and some other topics.
Yep.
I'll look forward to seeing what you have to say.
Okay, here we go, Leif. Hopefully this is seamless, right? There we go. Oh. Yeah. Let's do it this way. Right? There we go. Is everything looking okay, Leif?
Looks good.
All right, here we go. All right, so this is your DNR updates. A lot of them will be similar to last year, but I thought there's some interesting stuff here at the end that I'm going to talk about. So the first ones I'm going to fire through pretty quickly, but here's the general breakdown. I'm going to talk about our guidance document updates, our technical standard updates, and then some MS4 related updates that I think are more interesting, I guess. So let's move on. So first, what we're working on for guidance or where we're at. This is one I mentioned last year that we have guidance that is currently available for solar projects. And there's been, as you probably have heard or seen, there's been quite a few solar projects around Wisconsin. So we needed to develop a guidance to deal with post-construction stormwater. Because as you can imagine, it was somewhat, somewhat unique as far as how to regulate these solar fields from a post-construction stormwater standpoint. So we do have a guidance available now on the website. It's mostly promoting vegetation under and around the solar panels to provide infiltration and filtration. So that's what the guidance basically lays out, is some techniques to hopefully avoid having to put any kind of like permanent, let's say ponds or anything else in on a solar project. So we have that guidance available on the website. right now. The one that just fairly recently was put out for public comment and should be available shortly. Eric Rortfett is working on this one, is our post-construction modeling guidance. This is the guidance that mostly is appropriate for people that are getting construction site stormwater permits, putting together stormwater plans. There's things that questions that come up that aren't answered by either the code or the permit or our technical standards. So that's what this guidance is really important. I use it quite a bit for plan review. Anybody who's submitting NOIs should keep up on this guidance because it is, it kind of guides how you, in particular, calculate things like TSS control and infiltration and things like that. So there was an update that Eric did fairly recently. It covered some changes to WinSlam regarding biofiltration, also a section on filter strips. So we're trying to kind of we don't have a tech standard for filter strips yet, but there's quite a few comments that come up and people are trying to use it in WinSlam to take credit, but that raises some other questions without a tech standard. So there are some new elements regarding filter strips and a few other things. So it was due for an update. It was probably about 4 years old. So this is a guidance document that we do update quite frequently. So it should be available fairly soon when Eric gets through all the comments. So that's it for what we're working on guidance documents. We have several tech standards that are in the works, and I think I talked about this last year too, suggesting that they would be available already by now, but we're getting closer. So one of them is the dry pond tech standard. That was one that was asked for quite a while, and it's not the traditional old dry pond that was put in 30 or 40 years ago for detention. This is trying to design a dry pond to provide some water quality benefit, but it's not going to be something that you would go to as, let's say, equivalent to a dry or a wet detention pond, but it'll provide a procedure for getting some credit for a dry pond. So that tech standard is in what we call initial review. So it's sent out for a select group of people to make some comments, and based on those comments, it gets updated. So it should be, I've been told that it should be ready for public review coming up within the next couple months. So keep your eye on that. Obviously, we want people to look at it and submit comments. And then, through that process, it takes another month or two to get through all that. And so maybe sometime this summer, it would actually be published and usable. Sand filter, same deal. They've been working on together. But this is a practice mostly was generated because of the issues with the compost component of our filtration engineered soil. So you could design a standalone sand filter. This is actually a sand filter installed at the We Energies power plant in Oak Creek. So there's a few of these out there in the world already. But that tech standard, again, similar process. It's getting internal review, and then it should be ready for public comment coming up in the next couple of months. I did add in this picture of a iron aggregate product out of Chicago. Because part of the issue with the current engineered mix is that compost can actually generate phosphorus. So we're trying to find ways to counteract that. So the sand filter tech standard will make at least some reference to some additives, including iron filings that show some real good promise for phosphorus control in research done in Minnesota. And we've talked quite a bit with Andy Erickson. You've probably heard that name from the University of Minnesota. He's done a lot of research in this area. But I wanted to mention this particular product because any products that are added to water features technically need to go through a toxicity evaluation at DNR to make sure that they're not going to cause some kind of unintended environmental consequence. So this particular product is a iron filing product that has gone through the toxicity testing and could be used right now in Wisconsin. So showing a lot of promise. It's added in at a pretty low percentage to the sand. It could be actually added in the traditional engineered soil mix also. It's usually in a couple percent of the total mix. 3 to 4% of the total mix is this iron aggregate. But showing a lot of promise, even with a mixture that has compost and sand at controlling phosphorus. So we'll probably see a lot more of this, but I just wanted to mention this product because it could be used today in Wisconsin, but any other iron products would have to go through the same procedure for toxicity testing. There's another tech standard, the enhanced phosphorus removal tech standard. I think Leif's involved in this one. It was actually a single tech standard. Apparently now it's been divided into two. And this is primarily for wet detention ponds and chemical addition to cause additional phosphorus removal. So one's the flow weighted option. So this would be, similar to application of a coagulant in water or wastewater treatment, where it would be added during a storm event, proportion to the flow. And then the other option is episodic. So this would be basically like dosing a pond when there isn't a storm event occurring. And so the tech standards are developing procedures, how these chemical additions should occur in those two applications. So we'll see. This is probably more of an MS4 application, I'm thinking. Leif may have some more input on that, but that would be my thought on. I can't imagine like developers using basically permanent chemical installation technique, but we'll see how that plays out. So that's where we're at for our technical standard updates. Now I'm going to spend quite a bit of time, or at least some time, on some of the stuff we're working on in the MS4 permit world. So some really interesting stuff, and we'll see where it plays out. The first thing I want to talk about is something I've been involved with for the last year. This was a joint effort between DNR and MMSD to talk about urban soil health. So I think it's not a surprise that soils in urban areas are in pretty bad shape from either historic fill, compaction, poor vegetation quality. So we just contemplated the idea of what are the techniques that could take an urban soil and bring it back to something that is more of a water management practice. So like when you think about highly compacted soils, you can get quite a bit of runoff off of a impervious area that normally would infiltrate. So what if we in these urban areas develop the techniques to bring that soil back to its optimum management from a water standpoint, right? Both from volume and from pollutant. What could that look like? So we pulled together a group of experts. Some of these names may be familiar to you, and we asked them to volunteer time and just talk about what maybe a future tech standard could look like. How you could do, where the research gaps are, and doing some more research to quantify the effectiveness of some of these practices, and then doing some outreach. So this group helped us. We developed the recommendations document. And so I'm not going to go into all the details on it, but I did want to lay out a slide, and this just shows what the potential is. So this is where, a future tech standard could end up in quantifying the benefit of. Essentially, what this shows. This is a WinSlam model runs using a unit area approach from different source areas. So, running 1 acre of these different source areas over a year and seeing what the TSS loading is per acre. And what you can see is especially in WinSlam, if you use more of the compacted soil options, which is probably typical for most highly urbanized areas, that's a pretty significant pollutant load, more than I even would have thought on an acre basis. But what if you're able to take a highly compacted turf grass and bring it down to either low compacted or even like an undeveloped condition, which would be, let's say, restoring like a turf grass area to like a prairie, right? So it shows, we're talking, 80 to 90 to 100% control possible. So when you think about that as like a source area control, what the potential is, normally we talk about, especially for MS4s, right? We talk about having to put treatment practices in ponds and biofilters and trying to remove stormwater pollutants that have already been suspended. Well, what if you can control stormwater at the source? Is that a more efficient, effective, possibly cost-effective way of doing stormwater management? So this is, this may not be the answer for everyone, but I think a lot of municipalities may have some pervious areas that some sort of practices could be implemented that could result in significant reductions in discharges. So that's the idea. And some of the concepts that are out there in the world is suburban subsoiling. And we had an expert, Stu Schwartz from the University of Maryland, Baltimore, who provided a lot of the technical assistance on this group of the techniques that are available in the world to use. So this suburban subsoiling is essentially applying 2 to 3 inches of compost to the surface and then deep tilling it basically to 20 to 24 inches, and then revegetating it either, what could be with turf grass or with native vegetation. And, the interesting thing about working with Stu, he's very practical about this whole thing. It's like, he suggested, this doesn't create like a super soil. What it does is bring a soil back to its kind of optimum condition, prior to, all the urbanization impacts we talked about. So this is one of the techniques that we talked about. There's also some other techniques. This is just one of them. This would be more of something that you would possibly do on a residential site. It's essentially digging up the compacted soil and putting it back in a way that it's uncompacted. So if we have a future tech standard, it would lay out a number of different options. There's different aeration techniques. There's different aeration techniques in combination, let's say with like compost addition or sand to try to bring that soil back in some way. So future tech standard, hopefully we're able to do that, and it would lay out some different options. And then also if we're able to monitor these practices, actually quantify their effectiveness, we could establish some kind of credit system, which I think would be of interest to MS4s. There's actually a project. This is a project in West Allis that is recently funded under the Fund for Lake Michigan to actually quantify that suburban subsoiling technique. So Stu Schwartz submitted an application, and it was recently awarded a grant to actually take a plot of land where the city of West Allis had removed a dead end. So they removed this pavement section. They've already done that work. And what will happen is it'll be kind of like a parallel test site where, essentially half of it will be restored using the suburban subsoiling technique, and the other half will be just left as a kind of like a regularly compacted, restored area. And so what Stu will do using soil moisture probes and other measures is quantify the effectiveness of that practice, right? So then we can take that information and possibly use it in the future tech standard. Also use it as a demonstration site to show contractors how to do these techniques. So at least we're moving forward with a project that could supplement a future tech standard. So I just wanted to throw that out there. I know you probably heard, some of you have heard, we've been working in cooperation with Sweetwater also. So we've been talking about this a little bit, and there might be some interest in finding some other partners to do other practices on other pervious lands in the Milwaukee area, and also looking for sources of funding, which is always a challenge too, right? So I just want to mention that project. Another project that we started working on of interest to MS4s is a project where we're lucky enough to get a student intern to help with. So we've been contemplating the issue of long-term maintenance agreements for private practices that are out there in the world. I know this is part of the MS4 permit, especially if municipalities want to take credit for TMDL compliance using private practices. They need to have long-term maintenance authority and actually make sure these private practices are being maintained. And we just wanted to help in some way. So what our intern right now is doing is just getting a feel for what all the municipalities in Southeast Wisconsin are currently doing in this realm to somehow manage, the most difficult thing in the world, especially, ponds owned by homeowners associations and things. So, so we're doing a little background work. We're going to see what that tells us. We've also partnered with Sweetwater on this also to try to, we got a couple angles on it. First is just to establish what is the world like and what are folks doing, and then identify what maybe the needs would be. And, it's a difficult topic, from what are the best approaches legally, how do we help homeowner associations do this work, funding. It's a broad topic, and we've talked about it at this conference in the past too. So just stay tuned on that. I think we're going to need some help to try to maybe, ultimately maybe develop some sort of a guidance to help municipalities deal with this. But part of it is, learning what everyone's doing and seeing how we can make improvements. So stay tuned on that. We're going to need some help. We'd like to make some progress, hopefully, in this area. This is just some of the information I just wanted to put in with you to show like some of the data collection we're doing right now. We're actually putting everyone's ordinances in one spot to see what that tells us. We're also looking at all the different written programs that have been submitted to us under the MS4 permit to see what everyone's doing. And then we're also checking the actual activities that you guys have been doing as submitted in your annual reports for like how many private ponds are being inspected, things like that. So this is just an example of some of the data collection we're doing undertaking right now. Finally, okay, not finally, but another effort that you'll hear about, Lexi Pasante. I think some of you have heard from Lexi. She's one of our MS4 lead folks. She has started a project called the MS4 BMP menu. So what ultimately this is going to be is a web DNR website application where we're going to provide essentially examples for everyone of different practices can be done to meet your permit essentially, right? So different programs and practices and have it all in one place on a special website. So that's under development right now. Hopefully should maybe be available this year. But this is for the MS4s to have resources that you can go to if you're struggling to, say, develop an illicit discharge program or something like that, right? Or how you regulate erosion control on construction sites. So this is what we're doing right now. It'll be a website application. It'll have all kinds of resources, fact sheets, and other things. So it's a pretty significant effort, but hopefully to have it done by the end of the year is what Lexi would like to see. So stay tuned on that. Should be a real great improvement for resources at least. And then finally, just give you a general idea of how MS4 TMDL compliance is going. I call it implementation trends. So, most of the communities that are in the Milwaukee area that are under TMDLs are doing some activity in this realm, right? So I just want to list, kind of what we're seeing for what folks are trying to do. I got a lot of this information from Lexi. One of the options, retrofitting existing ponds. There are some proposed new ponds and biofilters. This is that one. Actually, this is really timely. Some municipalities are still trying to obtain some sort of maintenance authority over private BMPs, and so hopefully you can help with that in the future. There are some stream bank stabilization projects proposed, some proprietary filters, and then actually this is an interesting one. I think Leif's going to get involved with this too, but Watertown is one of the few first communities that's actually going forward with a formal pollutant trading program for TMDL compliance of their MS4 permit, and it's become a challenge because we're trying to figure out how to deal with that from a permitting standpoint. It's a little complicated. But stay tuned on that. Watertown will be leading the way for how to actually incorporate pollutant trading into your MS4 permit. And I think that will wrap it up for me, Leif.
Great, thanks. I'm not seeing any chat questions, but I wrote down some of my own that I'd like to share.
All right.
Uh,
You're always good for those.
For the solar projects, since the vegetation is essentially a BMP and it's presumably being required by whatever community to fulfill ordinance requirements, does that then entail a maintenance agreement?
Leif, I should know more about this, but I don't. And I'm not sure what that. Yeah, I mean, I think that would be logical, right? That if a BMP is suggested in a plan, that it makes sense that there would have to be some kind of a maintenance. So I'm going to lean towards yes, but I haven't looked at the tech standard close enough to give you a definitive answer. But that makes sense to me that any practice that's being used to meet permit requirements should have some sort of maintenance plan. And that would include any kind of vegetated area, because obviously, right, if it's for some reason would start eroding or vegetation would die off, that would be, an issue that would need to be corrected, right? So it makes sense to me that it would have to be incorporated into a maintenance plan.
A couple questions from the audience here. For urban soil health, any feel for soils best to try?
That is a great question because again, we lead heavily on Stu Schwartz for this information. He did provide a table that showed that yes, there are soil conditions that are more, I guess, would be more effective than others, where you would get a better result. And I could provide that to folks, and it probably would become part of a future tech standard where a table would identify a different level of credit based on the soil type that you're either trying to restore or create. But that is a reality, is that, and he said that based on his research, right? I mean, not every soil type is going to show a major improvement. So that's just something that would be a consideration if you were trying to locate a site to try this on. But
Okay.
yeah, I could provide that information if somebody would needed it.
And then a question about retrofitting ponds. Is this for water quality or flood management?
Yes, so everything we do in the DNR stormwater program world is water quality based, right? So we are talking about doing primarily water quality improvements, and a lot of, with a pond retrofit, it might be a dry pond to wet pond, or it might be some an improvement to a wet pond. Let's say putting in a restricted outlet, but the focus is water quality, which is generally, storm events 2 inches and less.
Okay. And I had a question about the modeling guidance.
Sure.
Since this is a revision of an earlier version, does the DNR ever do a page where it lists the changes so that somebody doesn't have to go through
Oh,
side-by-side documents to see what's
yeah.
different from the older version?
The only way to do that, and actually I just checked the website today, the guidance that was public noticed is still on our website. So if you go to the DNR Stormwater website under publications, you can still download, even though we're not accepting comments, you can still download the public comment document, and that does have the revised sections highlighted in yellow. But we don't keep that. I guess at some point that document will be taken off the website and replaced with the permanent document, and there's not a tracking of the changes. So if you want to see it right now, you can go get it, but you probably should do that soon.
Okay. Um, and then as far as the enhanced phosphorus removal standard goes, maybe Jim Bachhuber, who's also on that committee, could provide a better synopsis than I could, but the two different standards are one for flow weighted dosing, which is where you set up something like a shed on at one of the infalls and add flocculant to the water as it's coming in during a storm event, and do it during every storm event. And the the committee realizes that that's a pretty expensive proposition, probably on the order of $70,000 to $100,000 to upgrade a pond.
Yikes.
Using that. So in reality, probably that's only going to be done by municipalities, or perhaps by larger like Foxconn or somebody like that with big ponds. The episodic dosing is where basically somebody would buy some flocculant, mix it up in a tank on the site, and hose it onto a pond, and that would happen once, twice a year, perhaps. So that's something that'd be a lot more feasible. But in that case, you're mostly immobilizing sediment already in the pond and stripping out the water column, but then the water column would get replenished by inflow the next rain event. Well, I think that pretty much covers it. So thank you very much, Pete.
Thanks, Leif.
And the next presenter is Paula Kalinowski. Paula is a professional engineer with 13 years of experience in stormwater management. She holds a master's degree from the University of Minnesota, where the characterization of nutrient loads recovered through street sweeping was the subject of her thesis. During her many years as a consulting engineer, she developed street sweeping management plans for several municipalities in the Minneapolis area, and served as a technical advisor for the development of phosphorus credits for street sweeping for MS4s with TMDL waste load allocation reporting requirements. Paul is a former high school science teacher and currently works for the MPCA as the content coordinator for the Minnesota Stormwater Manual. And Paula is going to be talking about design of street sweeping programs. So thank you very much for joining us very remotely. So I'll turn off my camera, and then I'll turn it back on when you've got about 3 minutes or so to go to give you an idea where the clock is at. So thank you very much, and it's all yours.
All right. Well, thank you all for joining me this morning, and thank you, Leif, for that introduction. I'm gonna, let's see, I'll get my slide deck set up. I was just told there's a melody that everybody uses when they want to share their slides. And it's, sorry, I think I've got the wrong screen, but it's like, I'll just share my screen now. Anyway. Are we good? Okay, so I wasn't quite sure where this audience was at in terms of what you know about street sweeping and whether it's something you're trying to implement. So I've got a pretty ambitious slide deck here. I touched lightly on a lot of things, looking at the science and the project that I was involved in for my graduate research. And for those of you who are familiar, there's actually a lot of street sweeping research from Wisconsin, both in the past and currently. And then we're going to look at some of the applications of that street sweeping research, tiny bit on what Minnesota has done from a regulatory framework, and then some questions. So better get going here. So from a source control perspective, street sweeping makes sense. This slide is focused on phosphorus, and that's kind of been the focus of our work in Minnesota because we have so many phosphorus impaired waters. And in Minnesota, and I have to admit, even though I actually live in Wisconsin, in Prescott, Wisconsin, just over the river from Minnesota at the confluence of the St. Croix and the Mississippi, I don't always keep up on the Wisconsin regulations as much because I work and have worked primarily in Minnesota and lived there for many years. But anyway, so this slide is focused on phosphorus. We enact ordinances and legislation to eliminate sources of phosphorus or try to eliminate things, pet waste ordinances, or, in these Minneapolis metropolitan area has a lawn fertilizer, a ban on lawn fertilizers that contain phosphorus and has for many years. There's some things that we can't do anything about, we can't change the weather or any deposition, but street sweeping makes sense. It's a good housekeeping practice that we can use to prevent pollutants like phosphorus and other nutrients and just in general sediment from getting into our storm water network. So looking back at some of the past research on this, it goes back even further than NERP, but that's really when the first big study, comprehensive study, was completed. And the research was not very promising. The NERP study looked at some sites in 4 states, I think 10 sites total, or I've got 17 there, so it must be 17 sites total. A lot of rain events, but in comparing they were looking at the event mean concentrations in stormwater runoff in swept and unswept catchments. And they did look at phosphorus. They looked at some metals. I think lead was in there. They're listed down at the bottom of this figure on the left in really small letters, but total suspended solids, phosphorus, nitrogen, lead, and COD. But they were not able to demonstrate a statistically significant reduction in stormwater EMCs associated with street sweeping. And there are a number of reasons why that could be, and that'll kind of come out as we go through a bit of this street sweeping research history. But one of those factors was that they set a pretty high bar for what would be considered statistically significant. And if you look at this graph, you can see, so anything that did produce any site, these are site averages, by the way, these bars, anything to the left here was an actual reduction in EMCs, and anything on the right here is an increase in after following sweeping. So it's odd because these sites that have increased, they're quite high. We see a lot of wash on the street due to the rain event, but there's actually more sites that showed a reduction than those that had this increase. And then, so this, again, street sweeping makes sense. If we can get the stuff off the street, it won't go into the storm sewer network. So there was a renewed interest in looking at this. In the kind of later 80s, 90s, 2000s, we had some new stormwater tools coming online. I don't know exactly when P8 was developed, but P8, WindSlam, these were being put into practice by a lot of municipalities. And so there was some interest in newer street sweepers with better sweeping efficiency. And you can find a number of studies that try to model the pollutant removal efficiency of sweeping at this, in these years, where you calibrate, you go out and monitor the street for street dirt buildup. You can monitor wash off using measured stormwater concentrations. And so you can have a buildup and a wash off function in the model, and enact street sweeping at whatever frequency you want in these models. And unfortunately, these studies still didn't have a lot of promise. Just seems to take a lot of sweeping to get much benefit. But some other studies showed some promise here for street sweeping. There's one from 1999, Washbush, Selbig, and Bannerman from Wisconsin, looking at runoff from different source areas in residential neighborhoods. And they found that there was a correlation between the overstreet tree canopy cover density and the concentration in phosphorus. So this was not a street sweeping study per se, but they did also look at the sediment on the street and found that where you have higher tree canopy density, you also have more nutrients in the sediments that collect on the street. And a couple of these researchers then went further in 2007 in Madison, did a very meticulous street sweeping study where they used paired catchments, or actually serial treatment. So they would have a year where they weren't sweeping, and they were calibrating their model and not model, but it was a calibration period. And then they would sweep and see whether there was a reduction in the stormwater EMCs that were measured downstream. Unfortunately, they also could not find a reduction, a statistically significant reduction in stormwater EMCs. But again, this was a very meticulous study, and because its methods were so well laid out, I guess, and it did actually kind of highlight it was easier to identify what they might be overlooking. And William Selbig, the researcher, the first researcher listed here, has continued to work on these problems. And they would be, biased in traditional stormwater sampling methods. Like if depending on where you place your sampler intake, you will see different kinds of sediment. And what do you do with things that would float in, wouldn't even be captured by a stormwater sampler? And then just that fate and transport of organic material that makes its way into the storm sewer network. So that's where this project that I worked on in graduate school comes in. Some researchers at the U had been following these themes, and there was a forward-thinking engineer in the city of Prior Lake who found that anecdotally, it seemed that water quality improved when they increased street sweeping around the lake, or so that was the report of the residents. And so this street sweeping field study was born, and I was recruited to help crunch numbers and lab data and work in the lab a little bit. It was a 3-year study with a 2-year field component. We looked at 9 different street sweeping routes. They were all about, I would say, 7 or 8 miles, something that took about a half a day to sweep. They varied. The 2 variables that we were looking at were the overstreet or near street tree canopy density. So we had those classified as low canopy, medium canopy, and high canopy. You can probably see the difference best by looking at this high canopy and low canopy picture. And then the sweeping frequency. So for each of these canopy cover types, we had a route that was swept once per month, one that was swept every other week, and one that was swept weekly. And then we sampled the sweeper waste, and we got a representative sample from each of those sweepings, which totaled 374. and tested that material for its nutrient content, its total dry solids, and not really any of the like metals or toxins, but really just focusing on this nutrient piece. And to do that, they had a unique lab method, a fractionation scheme that's a little different than what you might think of when you think of sediment fractionation. We usually think about that NERP particle size distribution, or just a particle size distribution into clay, silt, sand, fine sand, coarse sand. But we had to use a density separation to separate this organic matter that would float. So the material was sieved, and then what remained on the sieve, the 2 mm sieve, was washed and then separated. We had to sample that wash water to account for nutrients that had leached. And what we called fines in this study was anything that was less than 2 mm. So that's kind of a different terminology than what we might be used to associating with the word fines. So that was a very quick look at the setup, but we're going to go through a really quick look at some of the findings. So some of the key findings here, so the things that were measured were the total solids that were collected, and then those nutrient components. And there's definitely a seasonal pattern to the solids recovery piece. This is this graph down in the lower left. You can see a spike in the spring, which is when they started sweeping operations. And then the amount of solids collected each, I think this is actually kind of for the year that I've got this graph set up. It's the total amount collected in that month. Yeah, year 1, year 2, the total amount collected, whether it's, once, twice, or for all the routes actually. And then you get another spike in the fall. So for this study, they actually swept any time that they could. So if the snow melted, they got out there in January and February. So really, I think I should have lumped together January, February, March, because depending on what the spring weather was like in year 1, they couldn't really establish regular sweeping until April. That's where you see this big gray spike. And then in year 2, they were actually able to start sweeping regularly in March because we had an early spring. But big spike in spring, and then a secondary spike in the fall. No surprise, really, because that's where when we have the fall litter drop, so we get a lot of leaves. But I did notice, it's not as if things just drop down immediately. The amount of solids kind of tapers off into July and August, and then it picks up again. And that's what we saw with the phosphorus recovery. So if you just look at that from the amount of phosphorus that was in that material, there is actually a spike in the spring, and a lot of that has to do with residual vegetative matter that's left on the street over the winter. But then it tapers off, but it doesn't really drop down until July, August, it starts to climb here again, but July is the low point. And when you think about the spring, you get all these leaves and or you get flowers and buds and seed husks and things that fall onto the street, helicopters. And those all have a pretty high phosphorus content. And we did notice with that wash water that we tested, there was a real spike in the phosphorus concentration of that. So it's a material that potentially leaches phosphorus. And then finally, looking at that frequency piece, what I've got here, light blue dots are the routes swept once per month. Red dots are those swept twice per month, and blue dots 4 times per month or every week. And what you'll see is if you kind of go, we got canopy cover across the bottom, so increasing canopy cover and the amount of phosphorus. This one shows both that as you increase the tree cover, you get more phosphorus. That was also shown up here, higher canopy, lower canopy, higher canopy, lower canopy. And then also as you increase the street sweeping frequency, you actually do collect more material, less per sweep on average, but more overall. So this low canopy route swept once per month. We only picked up about 1.5 pounds of phosphorus for that year. But here on the higher canopy end and swept more frequently, it was 5.5. And then just one more quick look at that coarse organic matter. That fraction of the material always this is an average of all of the sweepings, but by month, so all the February sweepings, all the March, all the April. looking at that average, always contained more than 50% of the total nitrogen mass. Typically contained 40 to 65% of the nitrogen mass in the fall, and maybe 20 to 40% at other times of the year, a little lower in the early spring. And I'll just note our canopy covers really didn't get any higher than about 20%. And we do have areas in the Twin City, older developments that have much, much higher canopy density over the street than this suburban area that we were doing the field experiment in. And then finally, or maybe not finally, but the other thing we did was track costs. So I have a summary here of what we got from the engineer in Prior Lake, summarizing the labor and maintenance costs. These are from 2011, so they're a bit outdated. There's not a lot built in here for disposal of materials. They did not have a high cost associated with that at the time. They were able to compost anything with a lot of leaves, and they reused a fair amount of their material for fill. They were developing at the time. So that's a cost that sometimes is much bigger for people, but for some of the cities. But the big finding was it can be very cost effective, especially that high canopy at particular times of the year. And regardless of the route that was being swept, you can see that about 60% of the sweeping, so this is a frequency chart, number of sweepings, how many of them came in at a cost per pound, within this range for cost per pound of phosphorus recovery. So about 60%, those costs came out to be less than $200 per pound of phosphorus recovered. So, and I know this one doesn't show it, but that fall sweeping and high canopy, some of those came in as low as $24 per pound of phosphorus. And then finally, one of the products of that study, we developed a tool that was meant for planning. So for planning your street sweeping, I developed a number of regressions where you would estimate the mass. This would be an average. This material is highly variable. So it's, again, you have to think about this as comparing scenarios and using average number, what you would expect on average, but you can predict the mass of solids, nitrogen, phosphorus recovered based on a constant sort of base loading, a factor adjustment for the month, an adjustment for the frequency of sweeping. Are you sweeping, every other week, every week? And for the canopy density over the street. And, I could do a whole presentation on how those were developed, but we did develop this Excel calculator, and you could put in a default cost. It doesn't have a routine for you'd have to figure that out on your own, what the cost per mile is, but you could add that in and get a cost per pound of phosphorus based on the street sweeping scenario that you were modeling. And you do have to know a few things. You have to be able to estimate an overstreet canopy cover density. We'll talk a little bit about that. And these other pieces, curb mile swept, that's should be a relatively simple exercise. Just most people have digitized center lines or lanes of street, and you can estimate how the distance of what you need to sweep. So those are the inputs. The curb miles you're going to sweep, the average canopy in that area, average canopy density over the street, and then that cost per curb mile would be something that you'd have to calculate. And some of these are optional inputs. So that was done while I was a graduate student, and then when I was moving into when I moved into consulting, I got a call from one of the watershed district. I know you don't have watershed districts in Wisconsin, but one of the watershed district managers who had worked in Prior Lake at the time of that study, and he said, in my watershed district, I'd really like to implement a street sweeping plan that uses this science. So we had to think this through, and what we did, we looked at, this is the overall strategy that you would use for planning sweeping for water quality. you need to understand what your water quality concerns are, where are your impaired waters or your waters of concern or your priority waters. You should have a mapped drainage network so you know where everything is draining, which streets are draining to which water bodies or which BMPs. Center line data so you can estimate the length of sweeping. Tree canopy data, either digital or aerial. We have a digital layer here in the Twin Cities, but that's pretty rare. And then some metrics for estimating solids and phosphorus recovery, which would be that calculator on the previous page that I showed, or have since been some other tools that have been developed. And then you need to group your streets into areas that are relatively homogeneous with respect to the stormwater treatment priorities. Does it drain directly? Is it in a drainage area that goes to a water body of concern or not? Does it drain directly to that resource or does it go to a BMP? And then, you kind of layer on this canopy information where you have a lot of canopy density and it's something's draining directly to a water. That's a high priority for sweeping, right? And, this isn't necessarily the way that you're going to rank your priorities. You need to, have a sense of what's most important in your watershed, but you're essentially just laying that canopy information on top and identifying areas that would be relatively similar with respect to those factors. And then the strategy is to add sweepings in the late spring and fall when the loading is the heaviest. You saw those on the graphs. Takes more than one sweep in the spring. There's lots to recover in the fall. And then you kind of work your way into July, prioritizing those areas that are, of highest concern. We did this when I was working at Emmons and Oliver Resources as a consultant for the city of Forest Lake in conjunction with the Comfort Lake Forest Lake Watershed District. They submitted a grant application and received a grant to develop a street sweeping management plan. And they parlayed the findings of that into another grant application, which they then used to purchase a street sweeper so that they could implement the plan. And so what did that work entail? This is such a quick overview. Some quantitative assessments. We had to look at the city and kind of look at the tree canopy. We have a layer that shows that prioritizes vegetation over impervious. So you can see where it intersects impervious. So we had to look at the canopy density over the streets and the drainage characteristics, where they have BMPs, and kind of develop these zones where there's those factors that I talked about earlier: high connectivity, high connectivity, and high street canopy. And once we had identified these zones that had that relative homogeneity, we used my calculator to estimate, okay, how much can we recover from the street by sweeping just spring and fall, by adding another sweep, by sweeping monthly, etc. And then we thought, well, what you recover from the street isn't the same as a load reduction to a water body. So this is a big simplification probably, but still as good as kind of maybe as best you can do. We estimated what % of that material BMPs within that each basin would capture, what's the capture efficiency of those BMPs, and then we applied that to these load reductions to get an estimation of the load recovery, to get an estimation of the load reduction to water bodies, and did an estimate of the costs for developing an in-house program following what the engineer had done in Prior Lake and talking to the city engineer there, and found that this city could actually save money by developing an in-house program. They had previously been using a contract service. Anyway, I'll just go on. But all of this work prompted the MPCA, where I work now, to develop a street sweeping credit for MS4s. There's a calculator that they've developed so that MS4s can, determine what, based on the amount of sweeping that they've done and what that material, they have to get material weights, what credit they can get towards their waste load allocations. This crediting calculator was produced using some additional sweeping data from 5 other communities in the metropolitan area. and an additional 175 sweepings, including some from the Forest Lake area, because they caught wind of this effort and said, hey, we're implementing our street sweeping plan, and we could send you some samples to use to calibrate your tool. And that was great for us because we could check our assumptions. And so what I found was that we had here, the baseline sweepings, we estimated that they were recovering 70 pounds. And at the time that we did this analysis, we still had a portion of these two sweepings were still planned. But at that point, the TP recovery, 142 pounds, exceeded what we were predicting for this Forest Lake watershed. And within another watershed, we had the same thing. What we had predicted was actually, what we were collecting was actually greater than what was predicted. I think I'll skip that one. I was just going to go back to, again, this was the strategy, and I'll just let you know, here's a QR code if you want. There's the University of Minnesota has built on this research to develop a clean sweep program. So they have tools that help you to estimate what your recovery based on canopy and these other things that we've discussed. You'll find another QR code, including ways to estimate tree canopy too. There are tools for that. So there's help out there, and I'll just say on Wisconsin, Bill Selbig has continued to do a lot of research in this area, and I can't really, it's really interesting stuff. Another QR code, you should read his articles. And I'm also a alum of the University of Madison, Wisconsin, so can't overlook that. All right, I'm sure I'm over, but
No, you're
I'll take
doing great,
questions.
actually.
What's that?
That's very interesting. In retrospect, do you have any idea why those earlier studies were statistically inconclusive based on your experience with this study and application?
Yeah, well, a big part of it, if you look at Bill's work, on the integrated sampling depth, a lot of it has to do with that. If you're just there's two things. If you're just looking at one point within the storm sewer, if you're pulling water from there, you're going to miss some material. You're going to miss heavy material that settles out before it reaches the sampling intake, and you're also going to miss anything that floats or is just too large to get in there. And then the other thing, so that's one factor, but the other thing is that oftentimes this organic material was just kind of overlooked, separated out, and not really analyzed. And there wasn't a focus more on toxins, I think, in those earlier studies. And that's not surprising. That's closer to the Clean Water Act and rivers being on fire and everything. And we weren't perhaps, there was a focus on nutrients and eutrophication, but I think, that's a greater focus for us now because we've eliminated a number of things through our NPDES permit. And we really can hone in on what we're not able to, what we haven't been able to solve so far. Yeah.
Here's a question from the audience. Did you do any correlation to what wind slam modeling predicted versus the spreadsheet calculations you prepared?
I haven't done that, but here's the thing with P8 and WindSlam I don't know if WindSlam has since added any functionality, but WindSlam I think was calibrated from that 2007 study. And that study was also, they didn't really analyze they stopped before they had a lot of leaf litter in the fall. It was just getting, for various reasons, because of the way the study was set up and the way that they would estimate how well the sweeper had picked up dirt, it was problematic. And I think that they would separate that out, and it wasn't part of the analysis in terms of the pollutant content loads. So P8, uses a NERP particle. You can put in your own particle size distribution, but essentially Stokes' law. And that, you can't really use Stokes' law to describe a helicopter, that's floating, or other bits of organic litter that float. They just don't, they just don't model well. We've tried it actually in a recent study here on gross solids, but they ran into some issues. So still trying to perfect ways to incorporate that material into those models.
Will you be uploading a PDF copy of your presentation to the OneDrive?
I will, yeah. I'll try to do it on the OneDrive again. I did send you a copy just this morning, Leif.
Okay.
So I'll try to get it up there again, but yeah, it's
Great.
there.
Either one will work fine. So
Okay.
great.
Yeah, and I apologize if this was a little too ambitious. I know I just had to touch on a lot of things lately, but I wasn't really sure what people already knew.
I thought that was great. Really appreciate it very much.
Okay. All right. Well, thank you. Is that it?
Thank you.
All right.
Next presenter this morning is Stephanie Prelwitz. Stephanie is with the Green Lake Association. Stephanie's the Chief Executive Officer of the Green Lake Association. She's been that role since 2013. She leads the nonprofit organization dedicated to safeguarding Wisconsin's deepest natural inland lake. She has a MS degree in Biological Systems Engineering from UW-Madison and a BS in Biosystems and Ag Engineering from the University of Kentucky. Her background includes water resources engineering, watershed management, strategic planning, and nonprofit management. When she's not chasing her two young children, she enjoys gardening and being on, near, or in the closest body of water. So I'm going to turn it over to Stephanie. Stephanie, I'll turn my camera off when you're getting down to a couple minutes left on the clock. I'll turn it back on again.
Great. Morning, everyone. Happy snow day here. Speaking of two young kids. So I'm so happy to talk to you today about the work of the Green Lake Association and our rationale about the benefits and or the need really to look more closely at phosphorus interception when it comes to managing lakes. So my presentation, I'll touch on three topics. One is I'm going to be talking a lot about Green Lake, so I'll talk to you about the lake itself, its water quality challenges. I want to talk about how when it comes to the really substantial phosphorus reductions that many of us who are lake managers are facing, best management practices alone may not be sufficient. And I want to tell you a little bit about some of the innovative approaches that we're testing and looking into. So welcome to Green Lake. Green Lake's claim to fame is that it's the deepest natural inland lake in Wisconsin. Its depth is 236 feet deep, an average depth of 100 feet. And because of that great depth, Green Lake stratifies into a two-story fishery. So warm water on top, cold water on the bottom. And that great depth is a very strict water quality criteria, so 15 micrograms per liter. The lake is 7,660 acres. The latest calculation of the retention time is that it's about 15 years. I think it's so interesting to compare that to Lake Winnebago, for example. I believe I read somewhere that its retention time is closer to 6 months. So really lots of water flowing in at a slow rate leads to a long retention time. This lake is a glacial lake, so formed during the last ice age. Green Lake's watershed is within the Upper Fox Wolf watershed. And so for that reason, we are part of the Upper Fox Wolf TMDL. But I'm going to talk in a little bit about kind of how our few point sources and other challenges kind of affect the way that we manage the system. So zooming into that pinpoint there that you see on your map, this is the Green Lake watershed, 107 square miles. There are 8 named streams that flow into the lake. And I just want to point these out, some of these more closely, because I'm going to be talking about them later. So on the east side, you have Silver Creek and Dakin Creek that flow into the Silver Creek estuary. And the southwest corner, we have 3 streams, Roy, Wirchus, and Spring Creek, that flow into the County Highway K Marsh. We have one outlet, the Puckian River, that flows northward to the Fox through Lake Winnebago and ultimately discharges to Lake Michigan at Green Bay. I think very interestingly, we only have one point source in our watershed that discharges within our watershed. That's the Ripon Wastewater Treatment Facility. And generally, that treatment facility has been meeting its water quality standards. So, I think in about 2014, they were even awarded as one of the best wastewater treatment facilities in the state. The Green Lake wastewater treatment facility is located and discharges outside of our watershed, and the sanitary district, which loops the majority of the lake, discharges outside of our watershed. So both of those are kind of doing us a water quality service. But when it comes to looking at point sources versus non-point sources, there's really one that we're working with, and that one is doing a pretty good job. When we care about the lake, of course, we care about the watershed, and our watershed happens to be largely agricultural, so about 65% agriculture, and that affects the way that we manage this lake and watershed system. We also invest a lot in high quality data. So you can see here, all of the blue dots are U.S. Geological Survey gauges. We also work with the USGS to measure within the lake itself on a monthly or bi-monthly basis. And we have such robust data for this lake. I think it's so interesting that we have data going back to 1905. So Burge and Jude, who are the founders of limnology, made the trek from Madison to Green Lake, and we have actual data in our long-term data set from them. A history of DNR citizen science data. 1981, the U.S. Geological Survey Stream Monitoring Program begins and then expands to the lake in 2004. Now, I don't want to say that the Green Lake Association is responsible for this, because only very recently we made investments. We're paying now $90,000 a year for this data using donor funds. But it really is possible because of a partnership with the U.S. Geological Survey as well as the Green Lake Sanitary District. So I want to make sure that those partners get credit because it's due. From that robust data, I'm going to talk a little bit about a diagnostic and feasibility study that the U.S. Geological Survey did in partnership with the Green Lake Association. But we found that on average, Green Lake is receiving about 20,000 pounds of phosphorus a year. Now, the majority of that is controllable loading, external loading. So what is that phosphorus doing to our lake? Well, it's really causing two primary water quality challenges, which we now know are related. One is that we have high phosphorus at the surface of the lake. You may recall that our water quality criteria is 15 micrograms per liter. Our 5-year average is 17.7. Now, that may not sound like a big deal. And if anybody is on Lake Winnebago, for example, you may be, wondering what all the complaining is about. But some of the calculations are that pre-development phosphorus concentrations for Green Lake were along the lines of 11 micrograms per liter. So, just these little shifts in phosphorus are making big differences for our lake. And that's a 5-year average, which happens to fall in a pretty dry period of time. So I suspect that these drought conditions are doing us a favor from a runoff perspective. The second water quality problem that we have is related to a metalimnetic oxygen minimum, a mid-lake kind of dead zone right at the thermocline. And it was for this reason that in 2014, the Wisconsin DNR listed Green Lake as impaired. The water quality criteria here is 5 milligrams per liter, and it's been generally worsening since 1905, going back to that data set that I mentioned from Burge and Jude. What does a metalimnetic oxygen minimum look like? As part of the U.S. Geological Survey's lake study, they sent a biofish, so a submarine that yo-yoed its way across the lake. And you can see that actual data here. Anywhere you see red, there's low dissolved oxygen. So you can see that dead zone is at the thermocline and stretches from one end of the lake to the other. And certainly you see low DO at the bottom of the lake, which we know is very common. So it is that metalimnetic oxygen minimum that's concerning. So 2014 comes, we're listed as impaired. Our impairment listing, the pollutant is phosphorus, but we didn't actually know that. And even if we suspected that it was phosphorus, we didn't have any sense of what was the scale of phosphorus reductions needed to remove the lake's impairment listing. So in, I believe, about 2016, we started a diagnostic and feasibility study with the U.S. Geological Survey and Michigan Tech. What I like about this study is that we kind of so this was done primarily by Dale Robertson and Corey McDonald. They worked together, but they also kind of worked in silos in that these were two separate approaches that came at the same problem. The U.S. Geological Survey relied heavily on watershed modeling. Michigan Tech collected more data and put together a lot of kind of ecosystem models. And we looked at three scenarios. How much phosphorus, first, is phosphorus the problem? And the answer primarily is yes. The scenarios were, what do we need to hit to reach our water quality criteria, to become oligotrophic again, or to remove the lake impairment? And I'm not going to go into the details of that, but I have citations throughout my presentation. So if you're interested, you can certainly look into that more. But as one example, the diagnostic and feasibility study found we needed a 60% reduction to remove the lake from the impaired waters list. Now, if you look at our lake management plan at the time, it said we needed a 10% reduction, which was based absolutely on absolutely nothing. No water quality modeling or anything like that. So for us, this was a real wake-up call that required our organization to totally shift. And we realized that our challenge was every pound of phosphorus making its way to the lake, we had to come up with ways to cut it in half. And that was much different than a 10% reduction. And so completely rescaled our organization. And since that time, because we've used data and science, and I would say good storytelling and communication, we've been able to scale up our organization to try to tackle this head on. So when you're looking at a 60% reduction or any type of phosphorus reduction, what do you have? Of course, you have point sources and non-point sources. And we often talk about these in terms of sticks and carrots. But you'll recall that we have one point source in our watershed. That's generally meeting its water quality criteria. And so for watersheds like ours that are primarily agricultural and not a lot of industry around, we really are working under a voluntary framework to hit these ambitious phosphorus reductions. And so we are doing all of the things that you want to do when it comes to those types of non-point source approaches. And certainly we can scale up, but we have a 9 key elements plan, a watershed management plan that opens the door to federal funding. The Green Lake Association used donor funds and purchased a no-till drill with a prairie seed attachment to allow farmers to interseed cover crops. We sponsor 2 farmers as part of the Upper Foxwolf Farm Demo Farm Network. We host field days. We sponsor stream restoration. We remove with the Green Lake Sanitary District carp from the lake. We help underwrite the cost of best management practices. And in just one example, in last year alone, our Green Lake management planning partners received over $1 million in best management practices. So hundreds of best management practices have gone in our 107 square mile watershed. But these are all carrots. These are all voluntary. And certainly we try to sweeten the approach rather. And we try to make these free. We underwrite the cost of them. We take the sanitary district takes on maintenance, but this is voluntary. So we started to ask ourselves a few questions. Are we really going to be able to install enough best management practices, often voluntarily, to hit that 50 to 70% phosphorus reduction? How does climate change affect B&P effectiveness? I know that Steve Carpenter and others in Madison talk about kind of the treadmill effect, where you're having to do more and more practices just to stay in the same place, much less to try to make a 50 to 70% reduction in phosphorus. Also for us, Green Lake's long retention time is both a blessing and a curse. It's a blessing because it shields us from some of these water quality degradation pressures, but it also means that we're working generations ahead when we're seeing warning signs, we're trying to respond to them. That change doesn't happen overnight. And I think very tellingly, and this is a genuine question, so I want to hear from you and I want to learn from you. Can we think of an example where we have installed in the state of Wisconsin, in the region, the nation, have we installed enough best management practices where we have measurably improved a lake's water quality? Now, certainly these BMPs are fulfilling an important role when it comes to kind of edge of field treatment, when it comes, to keeping sediment on a farm field. But these best management practices were often designed during the Dust Bowl to, prevent soil from blowing all the way to the doors of the White House. Where have we been successful in using them to clean up our lakes? I've been able to find one example in Wisconsin that is in Deer Lake in Polk County. This is an 812-acre watershed. I'm sorry, an 812-acre lake, a 5,700-acre watershed. And after spending $1.3 million for land acquisition, best management practices, a very engaged land trust there, they were able to reduce phosphorus by 53%. But I really am looking for success stories everywhere. So if we go to the other places that are kind of wrestling with this, Chesapeake Bay did a comprehensive assessment of decades of work, and they're saying, man, this is tough news. Existing programs are likely to produce the scale of reductions needed. Dick Osgood wrote a paper, and he found that after, that this strategy of using best management practices has resulted in a lack of progress in lake management. Closer to home, the U.S. Geological Survey did a assessment of the lower Fox system and found that, yes, BMPs make a difference, but none of the scenarios that they tested are likely to hit the TMDL targets. And so I ask, I'll say first that, of course, best management practices are essential to reduce the root cause of phosphorus loading. They play an important, critical role. But when we're trying to improve water quality, this voluntary approach, acre by acre, farmer by farmer, field by field, is that really going to get us to where we need to go to save our lakes? And so I would offer that this model of using voluntary adoption of these tools are not going to yield a 50 to 7% reduction in phosphorus or whatever that may be. So we have to broaden our approach. In Green Lake, we believe that using new innovative tools that have success elsewhere, but I think aren't widely applied in the Midwest, need to be looked at more closely, intercepting phosphorus before it reaches the lake. So I'm going to dive into why I think that the Green Lake watershed can serve as a model for this, and really provide, we're actively working on this now, but hopefully we're anxious to share what we're learning so others can learn from us as well, but also want to know what others are working on in this field so we can learn from you. So from that diagnostic and feasibility study that I talked about, we started to absorb that 80% of our phosphorus of this 107 square mile watershed really flows through two primary points of entry into the lake. 80% of our phosphorus through two inlets. And so can we use those phosphorus pinch points and other pinch points throughout our watershed as places to potentially intercept phosphorus? These are the systems themselves. And when you look at that watershed and you look at these bridges, you think that the possibility is there. These inlets are certainly showing that they are working hard on our behalf, but need some help. So you can see the Silver Creek estuary on the east side of the lake. The green you're seeing is duckweed growing. There are times when you'll see 100% coverage of duckweed in this system. And the County Highway K marsh, certainly you can see that there is likely an internal loading problem, a degraded marsh happening. So we're looking at phosphorus interception. We're considering phosphorus interception at two scales. So we take that southwest inlet, at the main point itself, but also at smaller sections, potentially on agricultural retention ponds. I'm going to talk about both of those now. If we think about kind of the larger scale, where are global success stories of this? Certainly, there are, in terms of sediment activation, using alum or other products to cap internal loading in our inlets is something that needs further study. Using the streams themselves as points to intercept phosphorus through some type of alum injection system. The example I give here is Lake Rotorua, but we have other successes. There's been lots of work done here with Harvey Harper and others in Florida. and elsewhere, and even nutrient reduction facilities. So for example, I think Brown and Caldwell worked on the Dixie Drain project in Boise, Idaho, rerouting a portion of a stream, basically sending it through a wastewater treatment facility and sending that cleaner water into the stream. Now, obviously, these are different scales. They come with various risks and operation and maintenance, but we want to know what's on the table before we kind of write something off. Is it possible? Certainly, we don't think that we have all the answers. And so last year, we partnered with the Water Council and we conducted a request for information process where they used their global network to reach out for potential solutions. So we're still combing through that. We received something like 20 proposals and 600 pages of material that we're working our way through. And we're also excited to launch a science advisory panel. So we're, and then very near future, going to be reaching out to some of the national experts in phosphorus interception so that we can talk about our unique lake system and get advice there. And of course, you know, there are some questions that we need to answer. What is the DNR permitting process here? Especially if we're talking about an alum injection system, some type of injection system. My understanding is this hasn't yet been done in the state of Wisconsin. It's been done elsewhere, but certainly we need some clarity there before we proceed. Lots of question about what to do with the flock in this type of system. How do you collect it? How do you dispose of it? You know, there's an ongoing debate about whether that is or isn't necessary. Certainly need some direction there. And of course, considering the long-term operation maintenance of these types of systems is important. Looking now at more of the field scale approach. So the green dots on this kind of schematic. One of the projects that we're working on is a capture structure. So 2 years ago now, we installed this the capture structure. We retrofit it to the outlet of an existing agricultural retention pond. And so this system will treat 96 acres. I'm happy to be partnering with Kaiser & Associates and the Green Lake County Land Conservation Department on that. So if we zoom in to that capture structure, if you were to open one of those boxes, you can see the inside here of this system. So all the, you know, after that runoff is held through an agri-drain system for 24 hours. We send it through this capture box. It's full of alcan media, which has been shown, you know, to have over 50% soluble phosphorus removal. So this one pond, we estimate, can treat about 50 pounds a year. May not seem like a lot, but when you think about that we have 50 ponds in our watershed, you can start to see that this could be a possible approach. Is this a long-term solution? Absolutely not. Is this a Band-Aid? You betcha. But isn't it better to be proactive when it comes to managing our lakes than waiting until we hit this ecological tipping point? And now we're trying to reverse the clock when it's much more economically and economically challenging. So some of the key takeaways then from this. Best management practices alone, and we're not going to BMP our way to a cleaner lake. So I think it's time that we start to think about broadening our approach. We believe that phosphorus interception may play a role, and we're really trying to actively serve as a model for identifying some of these strategies and certainly trying to test them in the Green Lake watershed. We think this is a very doable scale. You know, 107 square miles is enough to be I think a scalable system. So where we can take what we've learned and apply it broadly elsewhere. So with that, I'm happy to have some questions that anyone may have, answer questions.
Sure. Have you been looking at legacy streambed sediment phosphorus and perhaps like Dane County's Suck the Muck program as a possible source and solution?
We have. So one of the projects that I didn't mention is that, especially on Roy and Wirchus Creek, both of those systems were found in the entire, I think, 5,900 square mile TMDL area to be some of the worst, top 10 worst phosphorus concentration kind of hotspots. So we targeted that sub-watershed and did a stream inventory. So walking, using drone footage every mile of stream, identifying erosion hotspots. Now, my understanding about the Dane County system, for example, Dorn Creek, is there were times when the people who were in the field were kind of up to their elbows in muck. We certainly didn't find any instances of that. So at the moment, we're looking more at stream bank stabilization, stream restoration, wetland restoration, and less relying on kind of a suck the muck approach for the streams. Now, for the kind of inlets themselves, certainly kind of those approaches are on the table, but we don't have any direction yet.
Here's a question. The GLA is a volunteer association, if they recall correctly, not a lake district. How are you funding these initiatives?
Yeah, great question. There are 15,000 lakes in the state of Wisconsin, about 500 lake associations, and there are 3, best I can tell, that have paid staff. And so we are one of those. So we are a lake association. We are not a lake district. So the majority of our funding comes through fundraising. And certainly we are actively exploring grants and rely on grants for a portion of our revenue. But we believe that nonprofits play a unique role here to be innovative and nimble, to test new strategies, because we're not a government entity. We can take a little bit more risk and try something new. We can't use philanthropy to fund these types of systems in perpetuity, but certainly we can use philanthropy to test them. I've been at the Green Lake Association for 11 years. When I started, we had an operating budget of $100,000. We now have an operating budget of $2.5 million. So we are excited to be, we're the largest lake association in the state of Wisconsin. I think we can, for that reason, not only is Green Lake unique, but I think the Green Lake Association is a unique resource that we want to use to improve our lake, but also be a resource for others.
For voluntary donations, that's an astounding number.
That's why I have so many gray hairs that have come in since I've worked there. It's amazing. And by the way, not every lake association can do that, right? So certainly we understand that. All the more reason that we want to be a resource.
Do you have installation and maintenance costs of the Alcan system for the agricultural pond? Were there cost benefit analyses done for different treatment alternatives?
So we're happy to have the capture structure installed. As it goes with these pilot projects, it was installed during a drought year. So every time it rains, we actively are checking the cameras and the gauges, the level loggers to see if it has water in it. So, we have ISCO samplers, pre and post treatment. We are ready to go. But did we... working with Kaiser and Associates, they recommended Alcan media. The cost of this, just offhand, it's something like $100,000, but that cost includes sampling. It includes the sampling equipment. And so I believe that when we looked at the cost to retrofit one of these ponds, it was closer to $40,000 to $50,000 was going to be a more reasonable a reasonable number, but we're anxious to get the data. I really wish I could share that, but we're set up to get the data, and we'll broadly share that once we have kind of a dollar per pound of phosphorus assessment.
What about geese?
On the lake from a phosphorus loading source?
Yeah.
Yeah, maybe you're wondering why was goose impacts on my phosphorus chart. Green Lake is a big lake, and so it's an uncontrollable source of phosphorus that we take into account in our phosphorus budget. And that was based off of a Ripon College study where some poor soul had to, utilize, follow geese around. And with a pooper scooper and assess them. So it's part of our phosphorus budget, but not anything we can do anything about.
Well, Stephanie, thank you very much for taking the time to present here. It was really interesting.
My pleasure. Thank you.
Okay, thanks. Well, we have a 15-minute break scheduled, so you can go out and replenish your coffee supply or get rid of the previous coffee. I'm going to turn off my camera. I believe Kelly from Wisconsin Land+Water has some advertising to put on the screen in the meantime. And we'll see you at 9:45. I think we may start with a real quick poll, basically who you are and what you do. So Kelly, I'm turning over the screen to you. Hi, Kelly, would it be possible to run our poll about the audience composition now? Perhaps while we're doing that, I can introduce the next speaker. So while you're filling this out, I'll introduce Jim Bachhuber. Jim retired from a 42-year career in water resources and stormwater management in April of 2020. He worked in both the public and private sector over his career. He remains involved in the water resources industry through volunteer efforts with the Wisconsin League of Municipalities, Wisconsin DNR advisory committees, including the Enhanced Phosphorus Removal Committee that I'm on as well, and local government committees. He also takes on special projects for clients seeking his services related to stormwater compliance and management. And Jim, I presume you were listening to Stephanie's presentation just a minute ago, and I know you did some work on Green Lake yourself back in the day. I was wondering if you had any retrospective comments on that.
Yeah, I really appreciated her comments on the I submit I am fooling around with my presentation. BMPing our way to some of our water quality targets, like the very high phosphorus control targets for TMDLs, I think is a very appropriate statement, and has been a concern of mine for a number of years. So I second her thoughts on that for sure.
Just very briefly, the results of our poll were that of the 137 people participating, 54% are consultants, 31% are municipal or county staff, 10% are DPW staff, 3% are contractors, 2% are developers, and 2% are other. So appreciate everybody doing that. So Jim, why don't you go ahead? Like I said before, I'll pop back up when you're getting down to about 3 minutes and to give you a signal that the clock is ticking.
Sounds good. Thanks, Leif. I think from that poll, I'm one of the 2% who's other. So those of you who've been around the business for a while know I've been doing this work for quite a while, but I am in the retirement phase, but still staying active as I can. So I'm going to cover some topics that some of the stuff has been discussed before. Maybe it bears some repeating. I listened to the programs this morning. I don't see any conflicts with what I've heard from different presenters, especially the street sweeping presentation by Paula, and because I'm going to touch on that in a little bit on my talk too. Is my screen sharing okay, Leif? Are we doing all right here?
Looks good.
All right, I'm going to get right into it. I'm going to cover 3 topics here. Just kind of general, broad stormwater, and my focus is stormwater in urban areas topics or understandings. And I'm going to cover these 3: first flush, watershed boundaries, and street dirt. What's in my hopper from street sweepers. And I told Leif that, I think I've got plenty of time here for the slides I've got. So if you've got a question during any one slide, raise your hand. Leif can break in and ask the question, and we can, address it right away if you wish. So, we all have heard this term, first flush. We talk about it all the time as being something that occurs at storm sewer outfalls. When rainfall occurs, the highest concentrations are always found in the initial stages of a runoff event. And, I've done a lot of monitoring with DNR and USGS and on my own. And yes, this can occur. Does it always occur? Well, I find that's not always the case, and there's several reasons for that. We all have this kind of cartoon or idealized version of a hydrograph from an urban area or from a watershed, and we all have these in our hydrology textbooks, where the rain comes down over a certain period of time. After a certain lag period, you get runoff at an outlet point, and a hydrodraft goes up, and then it comes down, and it's a very nice, smooth, curvy line. In urban areas, let me back up. This may be representative in a lot of natural areas, rivers, undeveloped watersheds. I think urban areas in many cases are a different story. Now, why is that? Let's talk about some reasons why I think it is the case. You take an urban area and there's a watershed, and that contributes to runoff to a storm sewer system. And that storm sewer system, of course, conveys the water to some kind of an outfall at a river, a creek, lake, whatever, wetland. And so the hydraulics of the system are a lot different than what you might see on any rural or natural type of watershed. You got this storm sewer system that conveys water from different areas of the watershed at different times, at different rates, and it may reach this outfall at different times and different rates, and not come in a nice, smooth type of a discharge pattern. The other thing going on and we all know this happens everywhere, of course, in watersheds, rainfall occurs in different patterns. It comes at different times, different intensities, different directions. It's raining in one area of a watershed, not in another area. Then later on, it rains down here, and it was raining up here before. All this affects, of course, the timing of our discharge at a measurement point, let's say an outfall here at a storm sewer outfall. So what happens when you measure that outfall is you end up sometimes with a hydrograph that might look like this. This is an actual hydrograph measured by USGS quite a while ago, but I think the principles still apply. Let's just walk through this graph for a minute here, and we'll kind of walk through the various lines. The red line here is showing cumulative rainfall over time. The rainfall starts here at 2115 on the 4th. It rains pretty intensely for a while. It slacks off for a while, picks up again, slacks off for a while, and then picks up again the next day, the next morning, 7 o'clock in the morning, some intense rain. So this affects how the discharge is reaching the outfall. So this blue line represents the actual flow of discharge, CFS, at an outfall. And obviously it's quite erratic because of the hydraulics and the rainfall pattern and maybe some other factors in that watershed. So the question becomes, if you're trying to capture a sample during this runoff event to measure water quality and get, let's say, an event mean concentration for TSS or phosphorus or whatever, well, where do you want to sample to represent what's going on with this kind of a hydrograph pattern? Trying to grab one sample during the rising limb, well, there's a rising limb in here, there's another rising limb here, rising limb here. Obviously, you're gonna get different numbers no matter where you grab across this hydrograph. Sophisticated sampling programs, of course, address this issue by sampling several times during an event, usually on a flow-weighted basis or other basis. So these yellow squares grabs water during different parts of the hydrograph. You can use some mathematics to then calculate what percent of the volume each of these sample points represent, or you can composite them and get an event mean concentration by capturing throughout the hydrograph. And so the first flush would not have given you a very good idea. The other thing I want to kind of point out here along this line with this first flush issue is sometimes there's unlimited sources. First flush implies that the initial rainfall washes off the parking lot, streets, roofs, etc., of the dirtiest conditions, and then as that storm continues, the streets become cleaner and cleaner, and thus less loading going on. Well, some places in our watersheds, and depends on the watershed, have things going on that essentially are never get depleted. We got heavy industrial areas, construction site erosion, industrial waste sites, and you can rain, for a day or more and never run out of source material to be discharging water to that outfall. So again, here's an example where first flush kind of starts to fall apart. So my point here is just to think about that this first flush phenomena in urban areas, you need to know more about the hydraulics, the rainfall patterns, and the watershed to come up with some conclusions there. Another quick topic I want to cover is this idea of the watershed. Obviously, we all know what a watershed is. It's a pretty basic concept in our work every day. And we think about a watershed like this, kind of like this cartoon I picked off the web here, with a neat divide, and the water all runs one way or the other and gets to a discharge point. And yes, that's certainly, I'm not going to argue about that. However, I think there's places, especially in our smaller urban areas, where we need to be really careful about watershed delineations and how we go about that. And this becomes really important when we're trying to monitor or model discrete urbanized areas. And let me give you an example of one site that we did a number of years ago. Very small site. It's simply a single parking lot, real urban area in Madison. And we wanted to monitor this because we wanted to sample this underground treatment device as a USGS operation again. And they were going to sample the raw water coming off the watershed through a storm sewer system before and after going through this treatment device. And one of the factors, when they set these up, they put in a rain gauge to measure the rainfall, and you can then calculate, of course, the volume of water coming off this watershed in order to calculate things like event mean concentration or pollutant loads on a per acre basis. So the watershed here is pretty simple. It's all a parking lot. It's all paved. It's got one storm inlet here, storm sewer inlet here, treatment device, and then an outfall that goes, to a downstream storm sewer system. And when we first started looking at this site, we wanted to know the watershed to the treatment device. Okay, great. So we started to look at the site plan that was developed when the parking lot was designed and built. And based on the site plan drawings, we came up with a watershed boundary of about 1.4 acres in area. And after some monitoring of flow and discharge at this point, you get you get some numbers sometimes that say, well, it seems like it rained a lot more than what was coming out the other end, or it rained a lot less than what was coming out the other end. What's going on here? Is our watershed boundary an accurate depiction of where the water's coming from to start with? So, like any good engineers, we sent out a survey crew to do a very detailed survey. These are 6-inch, half-foot, I'm sorry, 1/10 of a foot contour lines, and we shot, a lot of shots around and redrew the watershed, or the topography of the parking lot, and redrew the watershed boundary based on that topography from the survey. And we went from 1.4 to 1.15 acres in area. This got us a little bit closer, but there was still a lot of discrepancy between what we were measuring and what we were calculating based on this watershed area. Okay. So the next step we did was to, let's walk it more carefully. And we literally went out there and sprayed water to see which way the water was flowing within the parking lot, and drew our boundaries based on actual water flow at the edges around the drainage basin. And after spending a morning or a half a day there, we figured out the best we could a new watershed boundary. And now we're down to 0.93 acres. So we're at 33% difference from our first delineation. And the other thing I think we've noticed, and you may have noticed this too in your work, is that sometimes, depending on the intensity of the rainfall and direction of rainfall, water can actually come in from other sources. Sometimes the water is flowing in one direction, but the rainfall is intense enough, you may actually pick up rainfall runoff from outside an area that a less intense rainfall would not pick up. So my conclusion here is that, I'm going to go back, that especially on these smaller areas, if you need to figure out a watershed basin, a watershed boundary for monitoring purposes, or maybe some modeling purposes, you need to be aware of these micro variations that can cause significant difference in the drainage area. I think that's just something to be aware of, that these watershed boundaries, using topo maps isn't always going to get you there. The last thing I want to talk about, I'm going to put us back on schedule here for sure, because I knew we didn't have a full 25-minute talk here. I want to talk about street sweeping for a little bit. And this has been going on for a long time. Paula gave a good summary of a lot of the history and background of monitoring and trying to get at the idea of what are our street sweepers doing and how much pollution control are they achieving. Paula was focused, rightfully so, on the phosphorus issue. I'm going to focus more on the TSS issue, total suspended solids, because for better or worse, that's what in Wisconsin our MS4 permits and TMDLs are based on. And that's been a kind of a bone of contention for some people, that we talk about TSS as the goal for a surrogate pollutant category to meet for our regulatory purposes. And I'll get into that in a second and explain why that's such an issue, especially when it comes to regulatory compliance. So what do our street sweepers pick up? What's in the hopper? Well, the garbage and junk you see along a curb is a mixture of stuff, right? You got leaves and litter and pizza boxes and dead animals and mufflers and bricks and dirt, street dirt or sediment or particles. When you dump that out, you see a good sized pile of trash. It's always good to get that stuff off the street for a lot of reasons, including water quality. But of course, a lot of street sweeping is done for aesthetic purposes, to keep the streets looking better, and the public wants that. When you look at what's in these piles, and Paula got into this a little bit, I'll just get into it a little bit also. This is based on some data from City of Madison quite a while ago, but again, these are brush mechanical sweepers now. So I know that some of this may change a little bit. If we had data with the vacuum type sweepers, cleaners, this may change a little bit, but for now, we're just going to talk about the mechanical broom sweepers. The particles that are in the actual particle sizes that are in the hopper looks like something around this distribution. A lot of the particles are in this above 500, above 200, 70% above 200 microns, which is a good sized sand particle, kind of the breaking point. So that's what the sweeper is picking up, a lot of this debris and a lot of this gross solids, we call it. And an awful lot of it is in the sand and gravel category as far as particle sizes go. 80% of the material in the hopper is in this range of sand and gravel. Now, when you talk about TSS and total suspended solids, which is what the regulations are based on, the NERP particle size distribution, we've all talked about that. You get a different picture of the particle sizes in the stormwater, in the outfall itself. 80 to 90% of TSS found in stormwater is finer than the sand particle breakoff. It's the silt clay sized particles. And again, I say for better or worse, that's what our regulations are based on. When we say you need to get 80% of TSS control, we're saying you need to get 80% of this material. It's assumed all this material's already been taken out, all the gross solids, and you're dealing only with the finest material.
Jim,
And
there's a question. Is this
Yeah,
measured
sure.
by weight?
Nah, this is by particle size, and this is by, oh, that's a good question. Weight or volume is the distinction here. You know, I used to know this. If somebody in the audience knows for sure, please chat in or something. I believe it's by weight, but I'm not sure about that. So again, if somebody's got a better answer, I'd like to hear it. Okay, chip in if you got a thought on that. Let's see. So there's good reason for why the regulatory agencies, including DNR, focus on this. This is where most, first of all, this is the easier stuff to get out for one thing, but this is where a lot of the attached particles, metals, bacteria, phosphorus, nutrients, the PAHs are all in this kind of junk, right? This is where you find that material. And so if you ignore this part, well, you're not getting that. You're still missing a very important part as far as water quality is concerned. So, there's a good reason why you want to focus on this TSS control. But it does cause this disconnect between what's in the hopper of a street cleaner and what's not being picked up by the street sweeper, the difference. Now, I want to make a caveat here because I think it's an important point that Paula made. When we're talking about phosphorus, if we were going to focus on that, and DNR in Wisconsin has certainly spent a lot of time moving in this direction with the leaf pickup program and the leaf technical standard now that's out and available for use. The fall leaf pickup program has become very important for TP, for total phosphorus control practices, and leaf pickup, a rigorous leaf pickup program in the fall can go a long way to having a significant impact on phosphorus on an annual basis. But again, a lot of that material is not TSS. It's a different category of pollutants. So, are street sweepers helpful? Yes, of course they are. Picking up the trash, debris from streets, getting rid of gross solids, keep them from downstream systems, and some TSS reduction is certainly achieved with the street cleaners, not perhaps what we were hopeful of back, in the past. And then, as I mentioned, the whole phosphorus removal in stormwater through leaf pickup, fall leaf pickup especially, is certainly a priority and a critical practice to use in our bag, in our tool bag. So first flush, sometimes, not always, especially in urban systems, there's a whole lot of factors that go into that when we're looking at that, and this is important for sampling purposes. Watershed boundaries, I think they can move around depending on rainfalls, distribution, intensities, and the watershed conditions themselves. And what's in the hopper does not always equal TSS. It's a good practice, but there's a lot of other stuff in there that is not part of the TSS spectrum. I think that's all I had. Let's see here. Yeah. So I know I'm very early. I'm sure you're all sad about that, but maybe we can, if there's any discussion or questions or comments, I'm certainly open to those.
Here's some audience questions, Jim. One is Minnesota considers snowmelt, I think, to be their largest TP load. Are there any Wisconsin studies on TP load and snowmelt?
I am not aware of, I mean, we certainly have had sampling done, and Bill Selbig would be the guy to tap into. I've not seen studies that, at least in Wisconsin, I should say, separate out the snowfall, the snow melt with the rest of the year's loading. And as we all know, in Wisconsin, the wind slant file, all these target numbers we're talking about, the rainfall files that DNR issues do not include the winter period. It's basically a 9-month rainfall. And because of the problems with trying to model and predict loadings from snowmelt, I think that's a huge can of worms.
I know that Bill Selbig likes to use automatic samplers. Are there problems with running those in winter when you have freeze up?
Yeah, there can be, and I know Bill would many times they don't run them because it's hard to time it. If they get a spring thaw, they try to catch those. But yeah, you have to talk to Bill and other USGS type folks to get a more technical answer on that.
One person confirms that particle size distribution is typically by weight, which I would think makes sense.
Thank you. Appreciate that.
And there's another comment that the first flush term they believe was used in an EPA report from 1972.
That sounds about right. Yeah.
Water pollution aspects of street surface contaminants. He included a link to the document and also offered to share it if anybody wants to, and provided an email address. Both are in the chat if anybody wants to look those up or ask for a copy.
Thanks. And where this became, in my opinion, this is only my opinion, problematic was the amount of effort spent, especially on the industrial sites, the permitted industrial sites where they had to go grab a sample, and there's a very specific definition of when to grab that sample and how much rain had to fall at the outfall. These are for industrials, permitted sites. And, the approach or the attempt was to try to catch this so-called first flush phenomena at these industrial outfalls. And I question whether that effort was well placed. I'll just say it that way.
Here's another comment. I think this is from Wauwatosa probably. In the fall, my municipality comes by with pickup mounted leaf plows that push leaves into the back of garbage trucks with ramps attached. A lot of small leaf particles remain behind. How do these work for nutrient reduction?
Yeah.
I think how these is referring to the plowing stuff into trucks.
Well, there's also, I know the leaves get ground up and pulverized during that operation, and a lot of the smallest particles stay right there and get washed right down. And, and Pete Wood can probably chip in here, but, the DNR's leaf program is, you can't just push them into a truck and carry them away. There's in order to qualify for the higher level of phosphorus credit, there has to be an immediate follow-up with vacuum type sweepers to pick up as much as possible those smaller debris and leaf particles. And so, yeah, just the mechanical removal of the leaf itself is not accomplishing, some, but not a lot of phosphorus control, because that phosphorus just, or the water just runs through the leaves, creates a T, dissolved phosphorus constant levels, and runs to the storm sewer. So you got to get the smaller particles too.
In your graph of the particle size distribution and collected by sweeping versus the NERP. I was wondering, if fine particles get washed off more readily by storm events, if more frequent sweeping happens, does that tend to collect more fine particles because you're sweeping before it's had a chance to get washed away? Do you know if there's been any studies correlating sweeping frequency with the particle size distribution showing finer particles?
I think the answer is yes. I know there's been studies done with sweeping frequencies, and this is done in Madison and other places, right? Again, USGS monitoring, to figure out, what's the optimal frequency, and can you measure, any changes? And so the short answer is yes. There have been some studies in that, and I don't know the answer of, do you get more finer particles if you subsequently sweep more frequently? It kind of doesn't make, if you're using, especially with the mechanical type sweepers, doesn't make sense that you would, I think you can only pick up so much stuff, so much particle sizes, and you can't pick up the smaller stuff for the mechanicals. I'm sure the vacuums do, I know they do a better job. And as Phil's, I'm looking at the comments here from Phil. Yeah, the vac sweepers are certainly doing a lot better, and I think the DNR in Wisconsin gives credit for that through the modeling process if you're using high efficiency sweepers like that.
Well, we're right on schedule, Jim, so
All right,
we're doing great.
great. I'll stop sharing.
Thank you very much for your presentation. It's always interesting material. I'll look forward to seeing you on Friday.
Yeah, I'll see you if the snow allows us. Yeah, see you then.
Okay.
Thanks a lot.
All right. Thanks very much. Okay. Next speaker is John Lindert. John is a civil water resources engineer serving clients in Wisconsin, Illinois, Iowa, and Ohio. His career is focused on planning, analysis, and design of the following project types: stormwater quality and quantity management, MS4 permitting, green infrastructure, sustainable design, floodplain management, dredging, stream bank and natural area restoration, and park and recreational facility design. He's a past president of the Wisconsin section of ASCE and currently serves as the chairperson of the CSWEA/WI Watershed and Stormwater Committee. In his free time, John enjoys mountain biking and muskie fishing. And John is going to talk about Madison's complete green streets, enhanced distributed green infrastructure, and tree canopy. So John, it's all yours. I'll disappear for a while. And
all right, Leif, thank you very much. Today I'm going to talk about complete green streets in Madison, Wisconsin, which was a larger project that we contributed to on the enhanced distributed green infrastructure and tree canopy guidance side of things. The presentation outline today is going to be, we'll talk about a timeline, some project goals, street typologies, and overlays that were part of this, the decision-making process of how to get DGI and tree canopy into the street cross-section. We'll talk about our bigger role in this, which was enhanced DGI and tree canopy guidance in 3 different areas there. And then decision-making flow chart in the end. One thing to keep in mind here on the right is the complete green streets guide was led by Tool Design. We were a sub-consultant along with EQT by Design. EQT by Design did public engagement, and we did this report on the DGI and tree canopy. So to start out on timeline, going back to 2019, on the bottom left, City of Madison had a number of reports that they wanted to kind of pull into the work that we did, including an urban forestry task force report, a SLAM analysis, and green infrastructure for purposes of flood control study, noting that Madison had a lot of flooding back 2018 or in this kind of era, that they wanted to see if GI could have a real role in that or not. At the same time, EPA came out with a Green Streets Handbook in 2021 that we reference in our report, has some good information. And then Birchline Planning was working with the city to do a DGI codes project or distributed green infrastructure codes project to look at ways in which codes could help with getting distributed green infrastructure into city projects, which led to our report as a complement to Tool's larger report on complete green streets. So some of the project goals here, complete green streets overall. The city wanted a consistent process for planning, designing, building, and operating streets in a way that better reflects the community values, increases safety and equity. They wanted to ensure that the green infrastructure needs of a resilient city were met. And one of the big things was they wanted to guard against starting from scratch on each project, road project that the city gets into because of all these multiple competing demands for right of way in the city. They wanted a guide in terms of how to get around that. And you can see some of the values on the right for a holistic process that came out of this. Our role was to provide practical guidance related to DGI and tree canopy to assist with this decision-making process for the different street typologies or types, noting that the complete green streets came up with an array of cross-sections within the right-of-way, and we were tasked with trying to figure out how to help guide getting green infrastructure and tree canopy in the right-of-way, not in the watershed. So pretty distinct clarification there. And then another thing was to coordinate amongst the city departments and their different interests out there with the 7 or 8 different departments listed there, as well as coordinating with Birchline Planning along the way. From a street topologies standpoint and overlays, this is one of the big outcomes of the Tool portion of the project, where they wanted to look at your collector, local, and arterial streets, and then define those into boulevards, community, main street, neighborhood, shared street, or topologies, as it's known in the traffic world. And then on the right are the different overlays that help with decision-making. And of the ones listed there, we're in the tree canopy and green infrastructure side of things, and we'll delve into that in a little bit. This is more of again, a Tool deliverable here. And this kind of talks about, hey, we start a street project, number one, what do you do? Look at all these overlays and street types and look at this guide. And where, again, that red box there is the tree canopy green infrastructure, where we contributed information, but really the idea is to then look at all these competing interests, allocate space for things, and then get into design in a more streamlined process than they had before. Street tree guidance. Okay, so we're going to talk about suspended pavement systems and how that can help with this. So we're going to talk about some tree canopy criteria that the city is trying to meet, suspended pavement system description, and 3 different types of that, and then a side-by-side cost comparison was one of the things that the city wanted to try to look at to help them guide the different systems they might use. And on the right there is a depiction of what suspended pavement system is. It's basically a void space held up by some type of system that suspends the pavement and allows for trees to be planted and grow in an unconfined or uncompacted area or volume. Some of the design criteria, or some of the criteria we're trying to meet, was tree canopy priority, the existing tree canopy in the right-of-way, and looking at a tree equity score. The idea was that the city is right now at a 23% tree canopy. They wanted to get to 40%. And you can see the table at the right in terms of tree canopy priority, high, moderate, and low. To move here. So you can see high, moderate, and low relative to the tree canopy in the right away, but there's also a tree equity score. If you go to this website here, there's different quadrants of the city that you can come up with this tree equity score, which is kind of an interesting thing where there's like a lack of trees or abundance. So that weighs into that as well. And then another thing that we looked at was optimal tree size factors for the different street topologies that were out there. What is the optimal tree size? What is the recommended terrace width? What's the minimum terrace width for actual planting a tree without using a suspended pavement system, which ended up being 8 feet. And then, as you can see, some of the guidance was yes, maybe, or no on use of the suspended pavement. Another part of this is the suspended pavement systems are really ideal for compact urban environment. We had some pictures here of what this looks like on the left, Martin Luther King Jr. Boulevard, on one of the systems there that's being used, and then a proprietary system on State Street. Really, it promotes tree growth in uncompacted soils, like I mentioned. And if you connect it to storm sewer or underlying soils are conducive to infiltration, you could also use it to bioretention. Part of our analysis, the city wanted a side-by-side comparison to some of the competitors that are out there, manufacturers, Deep Root, Silvacell, Green Blue Root Space, City Green, Stratovault. City has used the first two, but not the third at this point, but they're all relatively well used in the United States. However, some of the literature research we did, there wasn't a lot of good side-by-side comparison on these units in some of the design guidelines out there. So the city wanted that. That's kind of what we kind of show here. On the bottom right is the different systems and different sizes where they're manufactured, what the material is, including is it recycled, stacking allowed, and interlocking, things that help you understand the systems without having to go every time and look back at them. And then the table 3 up here was looking at the tree size that you might sort of the engineered soil required for the different tree sizes, and to get at some standards of how big these suspended pavement systems might need to be. A non-proprietary suspended pavement system, this is that State Street example. Back in, I want to say it was 2008, the city did put in a system that's shown here in the cross section that had kind of a pillar in between the root balls, the trees, and then you pour a slab out to that pier that kind of sits in the middle. And the city, while it works, there were some drawbacks to it. And so they ended up starting to go to these proprietary systems, which they then found were super expensive. And then they wanted us to come up with a custom suspended pavement system design, which is a kind of a prototype or a concept design that we show here. And it's, if you look at the bottom left graphic there, that's a section view, and it's based on use of a more readily available concrete column, in this case, EX Pier precast column by EasyCrete, where you would put those in instead of these kind of plastic units, HDPE units, more readily available concrete pillar, and then you'd pour your slab on top of that and have the appropriate sizing. All supported by structural calcs from our structural engineers to make sure it would work. And then we went with a side-by-side cost comparison on all these. So another thing the city wanted is what are the true costs of these, and what could this prototype or concept come in at? So if you look at this on the left, we've got a delivered product cost and an installed cost on non-proprietary and proprietary. And I guess we can look at the installed cost of around $28 per cubic foot for the prototype we came up with. The State Street cardboard void form is what they called it. It was around $24. And then you can see the proprietary being much higher than that, with the deep root and green blue having bid tabs from city projects, and the Stratavault was more based on information from the manufacturer because the city hadn't done their own project with that. The other thing we looked at was permeable pavement and how that can be brought into any cross section in these different typologies. So we'll talk a little bit about it. Permeable pavement description, some of those types that are out there, system comparison, and some design considerations that the city wanted us to look at. One of the main ones being structural considerations, that the fire department had some question on use in fire lanes and other things where they have to operate their equipment. So I think a lot of you know or have used permeable pavement. There's a number of organizations that support these different uses, including design guidance and standards, as you can see on the bottom right. DNR has a lot of guidance that we all probably use. That's all referenced in this document to kind of get it in one place. And just a little bit of a comparison on some of these for those that maybe haven't, don't know a ton about it. And again, it's in this guidance document to let any user really understand this information. Pervious concrete, typical thickness 5 to 8 inches, 15 to 35% voids. You can get pervious concrete panels out there. City of Madison has used these on a pilot project on the far right there, along a kind of a parking lane area in a residential neighborhood. Porous asphalt, typically around 2.5 inches thick, 16 to 20% voids. And then permeable pavers and blocks, and permeable interlocking concrete pavers. Sort of a comparison there. And again, on the far right is the PICP Madison used on, again, that pilot project that they did some monitoring on, and Phil Gabler's done a talk or two on over the years. From a system comparison standpoint, at least in our guide here, we wanted, again, match permeable pavement use with some of these street typologies, and this yes, maybe, or no kind of criteria. And if it was a maybe or a no, where could you use it within the cross section? You might not use it in the drive lanes, but you could potentially go bike lane or sidewalk, parking lane, center turn lane, things like that. So we had some guidance in there to help on that end. Some other design considerations. The city wanted an overlay of where can we really feasibly put infiltration type BMPs. So we came up with a number of figures, but we also have this in a GIS app. These are more static maps that I'm showing here, but winter salt routes layer, do you or don't you want to be putting infiltration BMPs there? Figure 28, bad for GI layer. This is a layer the city had come up with a lot of different parameters, and it looks like everything's bad, but I think when you zoom in, it's not quite as bad. Looking at underlying soils and the like. On the bottom left there is the 100-year flood inundation maps that came from a lot of the studies the city has done from a flood control standpoint. And it's good to know that to try to do infiltration upstream of those areas, potentially to help with flooding. And then the bottom right is a some wellhead protection zones within the city. And what are some of the distances you want to start taking closer look at? Do you put infiltration BMPs there or not? With this little graphic kind of in the middle of that, showing the kind of the rising chloride levels on 6 different wells in the city where there's heightened attention to that. So this is a GIS layer, turn things on and off for all these different layers that the city's working with. I did talk about some of these structural considerations, and there's not a ton of information out there either about loads and things like that that are appropriate in use of these different permeable pavements. But we did have this table 9 and looked at various usage in various parts of the right of way, including looking at, is it compatible with the parking lane or pedestrian path, sidewalks, or even the motor vehicle travel lane. And there's some guidance out there on thickness of pervious concrete that you would use for different areas, easels that are out there on on asphalt, porous asphalt, and how thick you might go with that asphalt. A number of other things there that are kind of interesting to look at. Table 8 at the bottom right is looking at compressive strength of each of these systems, and then the fire department's minimum that they wanted 75 PSI strength. And when we look at this chart under compressive strength range, from published data that's out there and maybe some studies that we found, all of these systems in general have plenty of strength to support this 75 PSI fire department minimum. I did find some other numbers out there, fire truck wheel load and fire truck stabilizer outrigger load, that are higher than that, but also lower than sort of these compressive strength ranges that one would expect compressive strength on the permeable pavement systems. So that really quelled the fire department's fears of, not wanting to maybe use permeable pavement in fire lanes and other places where they, when they do review site plans and things. From a stormwater quality standpoint, permeable pavement, I think we all kind of look to the DNR technical standard, which has 100% treatment of stormwater that infiltrates in these TSS and TP treatment numbers of 65 and 35%. We also looked at some other studies that were out there to get a feel for what others were saying and doing that we list in the guide. Also, what came along with that was standard specifications that users could use for permeable pavement, as well as typical sections for consistency sake on city type projects. And as always, there's usage considerations and maintenance on permeable pavement, making sure that the pavement's vacuumed. What do you do with the snow, plowing pavers, and then some of the other concerns that the city had with some of these technologies are listed. And then you saw in some of those tables above, ADTs and easels and appropriateness for that. And now I'm going to get into the non-permeable pavement, green infrastructure, and how that again might be fit in the right of way. We'll look at DGI priority. We'll look at some of the types of bioretention, types of DGI, and some of these are the usuals that are out there. But again, it's fitting those into a right of way of some sort, not necessarily out on the watershed or outside the right of way. We'll look at a system comparison and some Madison design requirements and some design guidance documents that are out there for these as well. And then some decision-making flow charts that helped kind of pull this all together. One thing to note is Madison's definition of GI is generally a stormwater BMP having infiltration as a main function. So you don't see wet ponds here. You wouldn't probably anyway, since it's in the right of way. But we tried to focus on those, other than a couple in here, catch basin and Coanda effect screen, where if it just didn't make sense for anything infiltration wise, they wanted that in sort of the matrix of BMPs. So sure, there's DNR tech standards out there for all these things. And Madison has done a number of studies and has flyers. We did do some research on stormwater quality treatment. And of course, you can model this in WinSlam or P8. But wanted to see what others were touting in terms of TSS reduction, is what they wanted us to put in here. So you can see kind of the reduction ranges there in the chart. And then one of the bigger things was this DGI priority. On the left, you've got the no, low, moderate, and high priority. And then along the top were these, these figures that I showed before, as well as a couple of other parameters to help get a score. If you average these all together, you get a score on should we be putting DGI there or not. And I'm just going to read some of those along the top. The underlying infiltration potential at the surface or within 5 feet of surface, looking at some of the different infiltration rates that are out there to determine the priority, location in relation to that wellhead protection zone, and really some criteria there, location relative to winter salt routes, location relative to existing flooding during 100-year event, and then really terrace area available for DGI. The less terrace you have, the kind of less things you can do to some extent. And then lastly, on the right, stormwater quality need in terms of TMDL, reach shed, TSS, and TP reduction performance. High priority would be if you were less than 40 or 27% TP in one of those reach sheds there, because that was the level where the city can buy into Yahara winds after you get above that, and then kind of going down from there. Just wanted to take a look at some of these BMPs. I think you've all seen these, but these are the ones that we analyzed for terms of this report. Bioretention basin, bioswale, the city's terrace rain garden, and stormwater terrace. A couple of distinctions here. The city's been doing the terrace rain garden program for quite a while. That takes water from both the residential side and the street side, owned and operated by citizens, but subsidized through the city. Really, it's small scale bioretention. The stormwater terrace that Phil Gabler's kind of been playing around with on some of his pilot projects are similar to that terrace rain garden, but it does not collect water from the street. More of a depression in that terrace to intercept flows coming from the residential side. Traffic calming rain garden pump outs is another one here, also known as stormwater curb extensions. Couple of pictures there that can help with traffic calming are basically a bioretention basin, provides some aesthetics to a neighborhood, as you can see. Rock Vault, this is City of Madison specific. Again, that Phil's been piloting out at a number of projects. Again, trying to get something that you can do in the right of way. In this case, trying to get a infiltration and then excavation down to a sand layer there, as you can see on the bottom left. Vegetated filter strips, another one out there, taking flow off the edge of a street. Stormwater planter, obviously these can be put in, and it has a fair number of these are out there. Small bioretention basin, kind of like a stormwater or suspended pavement system without the suspended pavement to some extent. And the catch basin, the Coanda screen, city has done, well, everybody knows what catch basins are. If that's the only option, they are effective if you regularly clean them. And then the Coanda screen, city's done a number of these. These would typically be at an outfall, maybe downstream from a right of way. We've done one recently with the city out on the Beltline. And they're pretty effective, but again, you need to clean them. And there's some issues with vertical drop in order to institute one. So from a system comparison, again, the city wanted these charts that help guide you per street typology on the left there, and all the BMPs on the top. yes, maybe, or no, in terms of the characteristic of those and how they might fit within that type of street typology. And then on the right, the DGI type on the left again. And what is the minimum required width in the right of way to actually institute some of these? And then would you typically use them in the right of way or outside the right of way? A number of comments, and then sort of this relative cost to help guide some initial planning decision making. Another thing that we referenced within the report is a calculator that we actually put together for Milwaukee Metropolitan Sewerage District that's available on their website. That is on the right there. Kind of an array of the different BMPs, helps you do some initial sizing to, kind of built off of some of the calculators in the DNR tech standard. It's been helpful for some users. And then to pull this all together, because you saw a lot of tables there and a lot of things to consider, we put together this flow chart to help guide through the process. And if you look on the top left, it's tree canopy priority. Well, I guess first you start with street type, and then you go to tree canopy priority on the left, the different priorities there and the different types of BMPs that have trees, whether it be suspended pavement or traffic calming bump outs or stormwater planters. And then on the right is distributed green infrastructure and the priority using some of those overlays that we talked about before to guide you to a BMP or two, depending on what you come up with. And lastly, this is just a little further drill down on a matrix to help guide through the process as well. So with that, hopefully I'm somewhat on time. Open it up for questions and answers.
Sure. So since this guide came out, have any streets been, redeveloped and the guide been implemented? And if so, how did the implementation go?
Yeah, I'm not sure if any City of Madison people are on here. I know they're using it to help guide their processes. I don't know if they have started from scratch on a project with this. Since then, I haven't been involved in that step, but I know they're using it for sure to get started on new projects. I don't know any specifics at this point.
With the suspended pavement systems that you were describing, one thing that occurred to me is that when trees go into terraces after 20, 30, 40 years, they heave the pavement around them up, or, the roots
right
grow and they buckle the pavement. It seems like putting one of these systems in might reduce the likelihood of that happening.
Yeah, and they have grates over the top of them. I think you could, if you really needed to, as they grow, you could, I don't know, cut back the grate or take the grate out, depending on what you needed to do. So yeah, the heaving issue is really sort of taken away with this a little bit, or a lot of it.
You have a chart with the compressive strength of different materials. And one thing that occurred to me with pavers is that they're essentially concrete blocks, and they may have individually really high compressive strength, but if you were putting an outrigger from a fire truck down on them, the limiting factor might actually be the base material underneath, and
right.
the blocks may not break, but they might still mush down into the the stone.
Yeah, I think that on a design by design basis, you would get geotech information and determine what that underlying bearing capacity is, which is typically be above, I think, some of those fire department requirements.
There was one comment about proprietary systems often go through very expensive third-party verification, can take 4 years and hundreds of thousands of dollars. To be a fair price comparison, non-proprietary systems need to be put through a similar third-party cost.
Yeah, I guess as long as, I guess from a structural standpoint, they work. Okay. And you probably want to get some in the ground and see how they work, I guess. But we're not necessarily getting any performance out of this other than holding the suspended pavement up. And so components that are part of it would be per industry standards and things like that. So we're not trying to get any TSS or TP reduction out of that per se, unless I know the city has done some of that to allow water back into the storm sewer system, kind of like a bioretention.
Well, John, thank you very much. It's good to see you again.
You're welcome. Thank you, Leif.
Okay. All right. Our next presenter is William Ganwa. Who has worked in the fields of wastewater collection, stormwater management, and flood protection since 1984. He has received degrees from Marquette University, University of Kentucky, and the University of Wisconsin-Madison, all in civil and environmental engineering. After practicing consulting engineering for 25 years, Dr. Ganwa joined the Milwaukee School of Engineering full-time faculty in 2010, where he's now a professor and the program director for civil engineering. Dr. Ganwa is fluent in Spanish, having lived and worked in Mexico, Panama, and Peru for several years. So what is the Spanish term for stormwater?
Agua fluvial.
Thank you. So you're going to talk about green alleys. So
Yeah.
I'm going to turn it over to you, and you're the last presenter, so you can pretty much take as long as you like.
Well, I don't want to take all the time in the world. Let's see. I want to share my screen here, which there, it should be sharing now, correct?
Not seeing anything yet.
Not seeing anything yet. Well, let me try. Okay,
Now
that's
you're good. Yep.
all right. Very good. Okay, so we've been that presentation we just finished with was talking about, okay, so how do you make green streets? How do you well, what's out there? But I noticed in that in that survey of how many people were out there, it's like 54, 55%. What was it? A large percentage of you are consultants. And the thing is, you're going to have to design these streets. And one of the big issues is, most streets aren't dead flat. They've got some slope, and a number of them have significant slope. Certainly in Madison, there's tons of streets with significant slope. I graduated there, and I rode my bike all over the place. And I remember my single-speed balloon tire bicycle, working quite hard to go up and down these streets. And so how do you actually store water underneath these streets when you've got a significant longitudinal slope? And worse, how do you actually do it when you're dealing with an alley where you only have this limited width? So that's what I'm going to talk about. Here we go. So I'm really going to focus on the subgrade. Let other people talk about whether to use pavers or porous asphalt or porous concrete or whatever. I'm going to talk about issues, the materials investigation that we actually did, and then the development of a design tool and our findings when we use that design tool, and then finish up on a little bit on how this guidance was actually implemented. All right, my computer is actually, here we go. So here's some questions with subgrade design. Like you've got this longitudinal slope, and we put large stone in there. What size stone should we put in there? And should there be just one layer of stone, 2 layers of stone? Do we put in drain tile? How do we optimize the water stored in this underground? Now, we don't want the blue line, okay? So the blue line is where we've got a lot of storage volume, but we're not using very much of it because the water's just flowing through the practice very quick. We don't want the red line either, because basically that means the water is coming up through the surface, and we're potentially going to have problems. And basically, there's quite a bit of problems when you have water coming up through the surface from underneath it. And what we really want is something like the green line, where yes, we're storing water in it. We're storing just the right amount of water to fully utilize that subgrade design. But it's not coming up through the choker pores, or it's not penetrating the pavement surface. So how do we actually do this? So there's design guidance out there, like the US EPA Green Streets Handbook, which was mentioned in the previous presentation. And one of its challenges says steep slopes, challenge steep slopes. So what are the design alternatives and recommendations? Well, it says construct subgrade check dams, not dams, baffles, terraces to provide level areas for storage. The DNR standard 1008 says limited to 2% slopes. And then it suggests in its design guidance that you might want to consider number 57 stone for storage instead of 3-inch stone. So those are some design guidance. But heck, if I were if I were still in consulting engineering and I'd be trying to calculate how much reduction I'm getting out of this, I don't have any information. I don't have enough information to design this. Also, with that guidance, and if you're dealing with an alley, let's say this alley is in Wauwatosa. This is for Wauwatosa, and the alleys are 14 feet wide. How do you construct terraces or check dams when you only have one way in and one way out? If you have impermeable cores, how do you actually do that? You're going to be having to place some material, change what type of material you're placing, change back and forth to the types of materials are you doing. How do you drain down those cells? Okay, so you're going to put in little drain tubes through those cells. How big of those cells do you need to do? Just some major problems. So Wauwatosa came to me and asked if I would be able to help them out, and they were looking at doing a summer alley paving project, and this was February, so there wasn't a heck of a lot of lead time on this. And I said, sure. So Wauwatosa, their design process, what they would do is kind of a mixture of Autodesk, storm, and sanitary modeling. They go back and forth, and they use like EPA swim, and basically it was really clunky, and they had very little confidence in how they were actually designing the results of their designing. So, and there's the EPA swim modeling that they would come up. What depth storage relationship should they have for that subgrade storage area? What depth discharge relationship? How much porosity is in that stone? What's the hydraulic conductivity? Just all sorts of questions. So they came to me, and the first thing we did was do a materials investigation. So there's certain types of stone that are used for the subgrade. And the question is, what's the actual horizontal hydraulic conductivity of such stone? You can't just do a vertical hydraulic conductivity test. So we decided to build a model of the alley subgrade. And you can see that on the left. There it is. And we went to order ordered different types of stone, number 1 drainage stone, number 2 drainage stone, and also 3/8" chips, drainage stone, all open graded. And we put that into this flume that we constructed, and we had a manometer board, and we ran water through it, and used there's a certain analytical solution that you can use to calculate the hydraulic conductivity. And we were able to figure out the material properties, the hydraulic conductivity of the stone we actually use here in southeastern Wisconsin. Then we also needed to determine the porosity and gradation. What we did was we just took a standard 1 cubic foot bucket and we filled it up with stone, and then we measured the amount of water in it. And then we also did some sieve analysis and shook it up and determined the sieve analysis, so we got our material properties. And here's basically what we had, looking at the hydraulic conductivity in inches per second. And sure, we might have about 2 orders of magnitude, but it was certainly better than the published range, which was like between 0.4 and 42 orders of magnitude. So we actually had no real good idea of what the hydraulic conductivity of the types of stones we would use for the subgrade. So we got a much better idea of it with the 3/8" chips, the number 1 stone, and the number 2 stone. And porosity was nice. So we found that the porosity was pretty consistent, somewhere around 0.4, 0.42, ranging up to 0.51, much smaller range than the published range. So it gave us much better numbers to use in our design. We also did the sieve analysis and our cumulative percent passing, and we found in all of these there's very little fines in these stones, which is exactly what we were hoping. Now, the design tool approach that we developed was kind of this mixture of a hydraulic model and a hydrologic model. So, and Waukesha wanted this all in an Excel spreadsheet because their design engineers were familiar with Excel. They could use Excel. They didn't want to be going back and forth between different programs. So here's what we created was a hydraulic model to determine the amount of subsurface storage and water table profile at different discharge flow rates, discharging from the practice. That's analogous to using like HEC-RAS to determine flood storage in a channel segment. And then we had a hydrologic model that actually used storage routing. This is the storage routing that you use for detention basin storage, reservoir storage. Anytime you do any kind of detention storage, you're typically using storage routing. Well, we use storage routing with the storage outflow curves developed by the hydraulic model, and that's analogous using HEC-HMS to determine flood flow at the outflow of each channel segment. And it's all accomplished in an Excel spreadsheet with much better, say, theoretical justification than seat of the pants estimates. So we made a design tool assumptions. Now these are embedded into the Excel worksheet, but they could certainly be changed. We used a 1 hour first quartile Huff distribution storm. And you said, why did we do that? Why didn't we use a 24-hour storm? Well, the issue in Waukesha was overloading runoff to the catch basins and the storm inlets. And what they really wanted to do was slow that intense 1 hour storm. They wanted to detain that water so that they were avoiding that localized flooding in the streets. So really, the 1 hour storm was the design storm that they wanted, and the first quartile is what is suggested for use with the 1 hour Huff distribution. We got our 1 hour rainfall depths from NOA Atlas 14. Inflow to the subgrade from adjacent properties, and the surface itself was distributed uniformly along the length of the alley. That could be changed, but that for a lot of these alleys, that was a good assumption. We also assume that the alley surface and the choker course do not limit infiltration. Now, that may not be the case, but we are designing for the situation where there is no limitation by the permeable surface, and that wasn't the focus, the surface, the wearing force. The subgrade, we looked at having 1 or 2 layers of drainage stone, each with a uniform thickness, and infiltration rate to native soil either 0, that would be in the case where it was actually lined, or some specified infiltration rate. And then a weir and a downstream manhole controlling the water level at the downhill. So those were the basically design tool assumptions. Comes one single spreadsheet with 4 simple tabs: precipitation runoff, groundwater hydraulics model, and step 1, developing the depth, discharge, storage, and storage function curve, and then step 2, the hydrograph routing. So let's look at some of these here. The surface hydrology tab, we just decided to use the simple NRCS type hydrology with it broken down for impervious surface and pervious surface. So pervious, typically in the areas we were looking at in Waukesha, the pervious was typically around a 74, and the pervious surfaces were about 98. And then we just split it up 60%, 40% for this particular watershed that we were looking at. Time steps of 0.05 hours, and we're talking about a 3-inch storm in 1 hour. So we have the precipitation and runoff in this for this particular watershed that we were looking at, and you can see we get quite a bit of incremental rainfall. That's like 0.3 inches of runoff in 1/12 of it, 1/20th of an hour. That would be 3 minutes. So very, very intense amount of runoff coming to this practice. Now, the groundwater hydraulics tab, now that we know what the permeability is, the hydraulic conductivity, we can actually determine the profile of water flowing through this, through the surface. We're assuming that the flow rate is increasing as you go along the slope of the alley. Here we have an average 3% slope alley. We're putting in this particular case, 12 inches of actually it's 3/8 inch chips at the bottom, overlaid by some amount of number 1 stone above that. A number 1 stone is basically equivalent to a 57 stone. Our normal depth, this would be if we had the entire flow rate flowing through the alley. We would expect to get 93 inches of depth. All right, but we're not going to get 93 inches of depth. That would be if it were that flow rate going on for forever at steady state conditions. Downstream, we were limiting the depth to 20 inches. That's what the weir downstream would control the water level to. So in this particular situation, we have 621 gallons per minute at the outflow. The width of the alley is 14 feet or 168 inches. And we have the lower layer hydraulic conductivity of 5.1 and the upper layer hydraulic conductivity, that's actually number 2 stone, 24.2. In this particular case, we had no infiltration. It would be a lined alley, and we were using the average porosities of 0.42 and 0.46 for this particular situation. And what we see, that dashed blue line is the water table in the subgrade, and the dashed red line is that 12 inches, that lower layer. So you can see that we're actually getting, for this particular situation, we're getting a nice amount of about, I would say, somewhere about 30 inches of water in this situation, maximum 30 inches of water in the practice. So that's groundwater hydraulics, but we don't know that will actually be happening because it depends on the rainfall runoff curve. So here we have the depth, which is Y, the discharge, and when I say Y, that depth is the maximum depth in the subgrade. So what we're looking at is, because we know our subgrade has to be at least that thick, whatever that maximum depth is. And then we have the flow rate, and then the storage relationship, and they're all related by the storage factor. And if you're familiar with storage routing, the storage factor is what links them all together. So here is the hydrograph routing tab, where we have an inflow hydrograph and then the outflow hydrograph. So this is assuming it gets into the subgrade, and we have the outflow, and you can see that there is a tremendous amount of detention of this storm, even though there's a 3% grade, average grade in the alley. Okay, and we're getting a detention of like on the order of about an hour, close to an hour, to where we get our peak, before we get our peak discharge. So this is really key information, because prior to this, there was really no way to quantify this. We'd just be taking a shot in the dark, trying to figure out how much detention we were getting and what was the peak depth of water in this. So we had to come up with very conservative designs, and the conservative designs may not have provided very much benefit. So here's the testing of the design tool. This was an actual alley that was set to be reconstructed, and the previous design typical proposed section had a 6-inch pipe under drain, and most of the storage layer was 24 inches of number 2 stone, and on top of that 8 inches of number 57 stone with 7 inches of pavers. Well, with pavers on top, and then some borders, a 7-inch concrete border. So that was the previous design that Wauwatosa was looking to improve. So we did our testing. The drainage area was 1 acre with 60% impervious surface and 40% pervious grass areas. And this was our findings from the 100-year storm simulation. We would have had 6 cubic feet per second running off from this area, but instead we had a peak of about 1.5 cubic foot per second running off, with a maximum depth in that subgrade of about 28, 29 inches. And more importantly, we had a tremendous delay. This 1,800 second delay meant all the regular pavement, the peak of that storm already went through, and now the storm sewers have capacity for this additional water. So here is for our 1-hour design storm occurrence interval, we have a peak attenuation ratio of ranging from 4 to 9, and peak delays running from 24 to 54 minutes, which provides tremendous benefits for water quantity management. Now, permeable pavements also enjoy some amount of water quality benefits, but we did not quantify that. So key findings from this is, when we have steep alleys or steep pavements, now this can be done in an alley, it can be done in a street, it can be done in a parking lot, anywhere you're getting one-dimensional flow, basically. There's no need for an underdrain. we had a 9-hour drain downtime. Well, you know, the goal is 72 hours. We were draining it down carefully. A 2-layer design with the smaller stone on the bottom and the larger stone on the top. Now that turns design guidance upside down. Typically, you're putting the larger stone on the bottom and the smaller stone on top. But how would you design a detention basin? You never put the low flow orifice at the top. You put the low flow orifice at the bottom, and then a bigger capacity up higher and higher. And since the number 2 stone has a higher hydraulic conductivity than a 3/8 inch storm, you put that, there's 3/8 inch stone, you put that 3/8 inch stone at the bottom. And then when that fills up, you put a higher hydraulic conductivity stone above that, so that if the water penetrates into that second layer, then it can move more freely to the outlet. But you've got, in here, we've got that 12 inches of slowly draining stone. So that's really important. This turns design guidance upside down than what you normally see. We looked at a 1-layer design with just number 1 stone, and number 1 stone is basically an average of 1 inch stone, and number 2 stone is an average diameter of about 2 inches, but we're on top of 3/8 inch chips, and we go from a 1-layer design with a 3 to 4-fold reduction in peak flow to a 4 to 9-fold reduction. Our delay goes from is much longer, and more importantly, in that with just number 1 stone, we get little storage capacity used in the 1 and 2 year storm. It's really just designed for and little storage in the uphill 25% of the alley. And with the 2-layer design, we get substantial storage used in that 1 and 2 year storm, which is a water quality storm, by the way. So it actually protects the waterways, and we do use more storage in the uphill 25% of the alley. So it was implemented. We started the study in like February and came up with this, basically the summer design. These were implemented that summer for design, and Maggie Anderson, who was the chief design engineer for the city of Waukesha, did this design. So I'm taking information from here, and this is kind of a typical situation where they're rebuilding an alley, and what we see on the photo at the right is their previous design with a 6-inch drain tile running down the middle of it, that they questioned the validity of that design. And here is some photos of construction. You can see where, this type of space, it would be really hard to build these baffles or terraces or check dams or something like that. You just don't have a lot of space. We do have those concrete borders. That's the design way Waukesha builds their green alleys. And here's some folks at work working on those concrete borders. But we do have the full width of the alley for storage. So even though the permeable portion is less, the storage portion is the full width. And there they are working on the catch basin at the downstream end of the alley, and laying pavers, standard pavement paver laying. And anyway, with at the end, they now have 25 green alleys installed with 80,000 square feet of pavement removed and almost 1 million gallons of water stored. And that's how far they've gotten so far. And with that, I'd entertain questions.
I don't have any audience questions so far, but I'm hoping we'll put some in the chat. So the whole design was driven by quantity control. Was there ever any discussion about, is there any water quality benefit to this as well?
We did not look at that. That was not the intention of this, we realized that any water that infiltrates, you'll be capturing those solids in there, but that water quality was not the focus.
So in this design, there's a 20-inch weir at the bottom of the run.
Yes.
Was it assumed that there was essentially like a permanent pool behind that weir, or was it assumed that that was void space and it would fill up at the start of the storm event?
The idea is that we would put a weep hole underneath that to allow this to drain
Okay.
slowly.
Got it. Question from the audience, is the design spreadsheet available?
Yes, and it is on the website along with the presentations.
Okay, yeah, we will, like I said previously, we put our the PDFs of the presentations on the county website. And I believe we said we'll make that link available and we'll put your spreadsheet there as well, for sure. You mentioned the choker course, and I've heard that term, but I don't know what it's composed of. Is that also like 1-inch stone or smaller?
Well, it's like number 1-inch stone, the choker course. It's what you're placing the pavement on. So it provides a stable base for the pavement.
Is that usually 6 inches, 8 inches, a foot?
Oh, well, I'm just looking at the standard design for Wauwatosa. I can't just, here's their implementation and design and construction. I'm just looking back to what Wauwatosa had before. So they had their choker course was 8 inches of number 57 stone is what they used.
Okay. You mentioned that horizontal and vertical connectivity were different, and I know that in natural settings, due to layering of soil or deposition over time, that they can be quite a bit different. But why would they be different in this case here, where I think the composition is uniform either way?
It is it's different even if you have uniform material. If you measure horizontal hydraulic conductivity in the same material that you measure vertical hydraulic conductivity, you are going to get different numbers. In fact, the hydraulic conductivity changes with the slope of the alley somewhat. Even, if we were to take our flume and change it from a 2% slope to a 4% slope, we would get a different hydraulic conductivity.
Okay. Question, could you describe the liner that Wauwatosa used? Is it an impervious liner, or would it potentially allow some infiltration? I think I saw in your diagram, well, the one you're showing right now, it says EPDM.
Yeah, that's all I know is that it's an EPDM liner. They do that when they're close to structures. So if they're going, or if they have contamination, I think. But if they're close to structures, they will line it to avoid having water exfiltrate underneath structures.
Got it. Yeah, so it's certainly impervious then.
Yeah, especially like if there's a house and a basement. When I say structures, I'm talking about houses with basements right close to the alley.
Yeah.
They do not want to surcharge basements with extra water.
So it's like a polyethylene or
Yeah.
polypropylene or something.
Yes.
Well, that exhausts the audience questions. So appreciate very much, and we should thank your students as well, because I see they seem to have done quite a bit of the work.
Oh, they did, and that work was done during COVID, and it was undergraduates that did the work. We just had, so it was really nice undergraduate research that the students that the students did. They had a fun time, I think.
Yeah, I think for students to be able to do something that's tangible like that has got to be really rewarding.
Yes. Yes, and if people have questions, they want to utilize that design spreadsheet and they have questions, people are welcome to contact me.
Another comment says EPDM is basically the same stuff as roofing membrane.
Okay,
Well, thank you very much, and it was good to see you again. It's been a little while.
yes, it has.
All right. Well, that concludes our presentations for today. We'll be back here at 8 a.m. tomorrow. So I hope to see, so to speak, the rest, most of you at that time. So I'll wish you a good night, and we'll be back tomorrow morning.